Hey, morning, everybody. Morning. So welcome to the first in-person CHIL and the fourth annual CHIL, or Conference on Health, Inference, and Learning. I am Joyce Ho. I'm one of the general chairs along with Andy Beam. And what I wanted to introduce is the goal of CHIL, which is that it's to bring together a variety of disciplines at the intersection of ML and health. And of course, this includes research in ML, but also statistics, epidemiology, health policy, operations, and economics. If you've been with us the last couple of years, you've known that we've been purely virtual for the last 3 years. And so I'm really excited that we're doing this in person this year. Now, this year and last year's edition has been hosted by the Association for Health, Learning, and Inference, or ALI, or AHLI. And so in addition to supporting conferences like CHIL, it also helps with co-hosting datathons, workshops, and grand challenges for the ML and health communities. If you would like to join the ALI mailing list, feel free to fill out the form at the very end of this event, and we'll keep you up to date with all the events. Now, you'll notice that ALI, in fact, is focused on not only driving research forward, but building community, thinking about promoting education, and then also data. ALI also co-hosts another event, which is ML4H. This will be co-located with NeurIPS 2023 in New Orleans. And so please do consider submitting papers, serving as a reviewer, signing up for mentorship, and also reviewing. And then stay tuned for the location for next year's CHIL as well, which we plan to keep in person. This year's conference would also not have been possible without the generous support of our sponsors. This year's conference sponsors are ApolloMed, Dandelion, Genentech, Sage Bionetworks, Apple, and AI-Trix. Our organizing team has also been working extremely hard to bring you an exciting 3-day program designed to simulate discussion and thought, and it includes 7 keynotes, 3 invited talks on the state of ML and health, 3 panels, 3 intentionally contentious debates, 5 research roundtables, 33 accepted papers, 22 doctoral symposium participants, and 5 lightning talks. If anything goes well, credit goes to the organizing committee. If anything goes poorly, you can blame me and Andy. And then just as some note keeping, so the first 2 days will be here at the Broad Institute. We'll have a cocktail reception tonight. There are still some tickets available, so if you didn't sign up for it originally, we have some remainder, limited number. So please see the registration desk if you are interested. Tomorrow is also going to be here, and it'll be followed by an evening social at Microsoft. And so there's also additional tickets for the evening social. You would have to sign up by tonight, though. And then the last day, Saturday, will be at MIT CSAIL in the Stata Center. Now, before we get started today, I want to go over a couple of housekeeping rules. So the conference program is found online, but there are also some out in front. We have a strict zero tolerance policy for harassment and bullying of any kind. And by coming here, you're agreeing to the code of conduct and the community guidelines that we've posted on the website. If you happen to be a Twitter fan, please, and you're finding the material very exciting, please hashtag CHIL23, and we're happy to retweet it through our CHIL conference Twitter. The other thing is to hang on to your badges, as you'll wear the same one for day 2 and day 3. If you want to recycle the material, feel free to drop it off at the front desk if you're not coming back. And then just as a last note, restrooms are right around the corner near the food stand, so if you find yourself in need of that, that's where they are. So with that, I'm going to go ahead and introduce our first keynote. This is Dr. Dina Demner-Fushman. She is a tenure-track investigator at LHN-CBC. She's a specialist in artificial intelligence and natural language processing, focusing on data extraction and analysis for clinical decision support and education. Her research aims to revolutionize healthcare with computational methods to process and analyze clinical data more efficiently. Her work has significantly contributed to Medline and the OpenEye platform for biomedical image discovery. With that, I'd like to welcome Dr. Dina Fushman to the podium.
Good morning. So before we start, I have to show you the disclaimer saying that whatever I say is just me, not the government. And now I'll just dive into my favorite topic. I think everything is question answering. And to support my claim, here I have, that obviously scientific discovery starts with questions. What was very close to my heart was the questions that the clinicians have at the point of service. Because when I was starting in my previous life as a young doctor, I had lots and lots of questions that I really did not know even where to start looking for the answers. And when I found this work by people like Paul Gorman, and then there was these collections of questions that the clinicians asked at the point of service that went unanswered, I felt like this is it, and is there something we can do to support these clinicians? Because lots of work at the time was showing that the clinicians do not even look for the answers because they don't think they are there, because they do not have time. So the idea of that just-in-time and at place of service support for their clinical decisions was very close to my heart. And then later on, we started looking at the NLM customer services that were getting all these questions about their health. And there was a discussion whether we should actually give them the answers. But what developed actually is that people started looking for their answers online. And as opposed to clinicians, they always find an answer. The problem with this answer is that you don't know and they don't know and are unable to judge whether the answers are true and supportive or could be harmful. So that's the yesterday, 2004. I came up with this proposal to the NLM administration, saying that what we need to support all these questions coming from the clinicians, from the researchers, from the patients, but of course many, many others that are involved in healthcare, the administration and so on. We need a repository for informed decision making. So we will store all kinds of really great knowledge somehow derived, probably semi-automatically, and then when we have the questions, we will answer using that repository. Fast forward to today, I heard from one of my colleagues that, well, we're basically done. The large language models have solved everything. They already encode all the knowledge that we can possibly have, so we don't need all that structured knowledge anymore, and that's just it. Like, done. Look for new tasks. Well, maybe not so fast. Here's the chatbot that was deployed on May 31st to support the helpline. And on June 1st, it was taken down because it gave really harmful advice to people who are trying to eat healthy. So I think the future, the tomorrow, is in supporting the great things that the large language models can do with the knowledge that we have. And that is kind of where we need to be heading, but to learn from the past, from our leveraging of knowledge in the past, I will go over the original system that was knowledge-based, and then our tasks that we have today, and then the tasks for tomorrow. So what remains constant in that question answering is that we want to deliver reliable information at the time and point where it's needed. And we do need some annotated high-quality data, at least for testing of our systems. We also need maybe some for still fine-tuning or prompt crafting, whatever. And what is constantly evolving is the methods that we use to approach these goals. And also our customer expectations, our user expectations, because I think in the past we were all very happy with a list of relevant documents to look at. And now we really want answers, and we want good answers. So going all the way back to the beginning of automated question answering, the goals were formulated in this sort of white paper that said it has to be the system has to be able to understand the question in natural language. It has to answer quickly and succinctly and provide support for the answer. So in terms of implementing it in an actual system, that means that it has to be real time. It has to show somehow that it really understood the question. It needs to aggregate, summarize, generate the answer using all the evidence that it found. And it also needs to provide support on demand. So in clinical question answering, I started with answering clinicians' questions, and then I will show the system that was based on it, supporting decisions for interdisciplinary teams at the NIH Clinical Center, and just really briefly touch on questions that should be answered by the EHR, by the patient's record. So the thinking was that the clinicians will be able to look at these very relevant documents in that very first system, and they will provide the question in the right form, and the system will align the answers with the question. That was based on the traditional framework for question answering, where the question is represented as some kind of a known scenario with a frame, and that frame contains these elements that are relevant to the situation at hand. So in medicine, there is that evidence-based medicine paradigm that actually tells clinicians to formulate answerable questions appropriately, and then search for the good evidence, and then extract the bottom line advice from that evidence. So that seemed like that can be implemented, and more specifically, the question frame is what's known as PICO, or patient and problem that the patient is having, the intervention that the physician is planning, and the comparison and the outcome would be sort of that bottom line advice that the system needs to provide. Now, we looked that evidence-based medicine recommendations for clinicians to do it manually were developed in a series of articles for the 4 basic clinical tasks for treatments, diagnosis, finding what caused the disease, and the outlook for the patient. So we looked specifically at manually coding the ELI questions into these frames. And it turned out, of course, that the frames are not exactly perfect for every type of task and every type of question, but for about 80% of the relatively simple questions, they were working just fine, particularly for the treatments, because initially they were developed for the treatments. So where is the knowledge coming from? Of course, the knowledge is coming from the Unified Medical Language System that tells us when we try to populate these frames, say for what the problem is, the UMLS tells us what the problem is through the semantic types of disease and syndrome, and sign and symptom, and so on. And the UMLS also has some relations between these entities, which we are currently exploring and finding that the entity recognition based on the UMLS is very close to 100%, but the relations are really missing a lot. So go back to that system. We use the UMLS to extract the problems and the patient characteristics and the planned interventions on the question side. On the literature side, we used the same tools to generate the frame for the abstracts. And then this is sort of more detail for extracting the bottom line advice. Because unlike all the other 3 slots in the frame that could be used on the UMLS, the outcome, the bottom line, is trickier. So we really had to annotate some data. And the funny thing about it is back then 300 articles was enough to extract, to train our traditional machine learning tools and extract the bottom line advice. And then the frames, in a very traditional frame unification way, were aligned. The question frame and the answer frame were aligned and re-ranked. And then we also summarized the outcomes and clustered the articles by the problems and by the interventions. So that system was then, we showed it at the NIH Research Festival, and just by chance, people from the clinical center were showing their research in the poster right next to ours. And we started talking, and they said, we really would like to have that system at the clinical center to support the decisions made by the interdisciplinary teams in developing the patient care plans, because they were actually having some warnings that their care plans are not based on evidence. And that would show that they actually look at the evidence to support the plans. So they would, the agreement was that we do not de-identify their data. They will send the data from the fields that do not contain any personal information to us, to our servers. We will process them, and then we will send the answer page to the EHR to be displayed in the EHR. So this is the answer page that was displayed, and you can see here that the progress note in the top left box was processed to identify the problems and the interventions. We also pulled the interventions, the drugs from their drug lists from various places, supported patient education with evidence from Medline Plus, and automatically constructed the question answering system is populating the bottom box with the answers and the bottom line to summarize the article. That system was sort of used, but anecdotally more when there were no other people to ask questions around, so off hours during the furloughs that we had. But the usage was not, so it was up for 10 years. The usage was not growing though. And when we had the discussions, like what would you want to see so that you use that system more? The answer was that we still need just an answer, not the list of papers with even with the summary of the paper. We still do not have time to go over that list and sort of derive our own answer to support our decisions. We really need just one sort of summary of what's in there. And we were also thinking that, that will, again, the system that underlies that is 15 years old, so it should be upgraded. And based on the usage and the upgrades that I needed, we decided that we will discontinue this tab in the CRIS system and come back when we have something better to offer. So for the questions based on the patient's record, clinicians have really, really simple questions, like what was the last measurement for that patient, or how many times did the patient get some procedure or something. So currently you really have to go through all these tabs. So the hope is that we can do that for the clinicians and pull up the answer, connected obviously to the evidence where it came from. So when Kirk Roberts was in his K99 part, we started developing that approach, and then he took these to UT Health to continue, and I think he continues working on it. Switching now to the consumer health questions, we basically use the same approach, and the system is pretty good on answering simple questions. So I will focus on the questions that the system cannot answer and what we need to do today to answer these questions. So here's the one that we got from our Medline Plus logs. These are all the questions that we are using, are real questions that people type into the Medline Plus search box. And here's this: I have a hydroxys pill with this imprint and color and whatnot, and can I take this pill with Benadryl? So the system cannot understand what that is. Manual searching told me that, oh, that is that most probably that hydrochloride pill, 50 milligrams from that specific manufacturer. So we do, working with these patients' questions, we found that they misspell words in very interesting ways. So we developed a special consumer-oriented spell check that is publicly available. You will also notice that there is an anaphora or co-reference in that question where they are asking about that pill. So that is also very common. So we have developed another tool that resolves that. So we can actually now rewrite that question as, can I take that hydroxyzine with Benadryl? But there is still no answer because there are no exact documents that are saying that. So what you really have to do is then go up and look at what class these drugs are. And you can see that they're all, so the system will need to make that hop and reason that these are both antihistamines. And then if you rewrite the question yet again as, can you take two antihistamines together, then there is an answer from some source. Well, of course, there is also now trying to figure out if the source is reliable, but that is, again, the task for today. So where we stand today, of course, is these amazing results shown by all these large language models. And specifically, we looked at these 3 papers in detail. What was very nice, some of the questions that these systems were using are coming from our collections that we released, so we are very happy that these real-life consumer questions found it into the question answering benchmark. And also, MedPalm 1 and 2 did an amazing job on evaluating the answers manually by 9 physicians, which is great, but not really feasible for, and we can see that the GPT-4 paper just openly stated we can't do that. So if they can't do that, probably not too many others can do that. And it's not feasible every day. So the evaluation is still a very open and unresolved question. So, but we also have seen that example that the system had to be taken down. And we also see that in the analysis in these papers, the things that can go wrong. The system can, and there is a lengthy discussion on how to call that, but I think hallucinations is now even acquiring a new sense specifically for these mistakes, or, some people call those lies, but some generated facts that are not really true. It can only be also be harmful content. So as we have seen in that healthy eating healthline, the answers can lead to harm. And the answers can be biased. So these are all the questions that we have to work on today. Now, to evaluate if the system is doing that, the MedPalm team came up with with the framework for the evaluation, and it is very detailed. Is it factual? Is it can it lead to harm? And when we started looking at that framework for the ongoing task that we're having with the National Institute of Standards, we decided that we do not have our judges do not have the background to answer all these questions. Like, is there a medical consensus on the answer? Well, our judges are librarians, so they probably will hesitate to say, yeah, this is the medically correct answer. For that plain language adaptation of biomedical abstracts, we sort of simplified the manual evaluation that we will conduct. So we will just look at the completeness and faithfulness. Is what the system has translated from the professional language into the lay language correct according to the source and complete? Then we will also, but for the old systems, this is still relevant. Is it fluent? For any system, is it simple enough for the user to understand it? And is it accurate? So we just released the training data, and we will release the test set in August. So if you're interested in translating from the lay language to simple language, there is a task for you. The reasoning for that task is that, particularly for the COVID evaluations, we found that lots of answers for the consumers are only in the professional literature, and they cannot really understand the answers in that professional literature. So we do need to simplify. We just, another team just completed a task on summarizing the Medline abstracts into the lay language summaries, and the results will be presented at the BioNLP workshop in July. And then this task is sort of slightly different, because here the system has to translate every sentence, and then we will be judging the sentences that were marked as the answers. So how else can we mitigate these potential harms? So this is one of these questions where when we were just starting this research, the NLM director at the time, Dr. Lindberg, was very interested in the system, and he really wanted to see the questions people are asking. So when he would see a question like that, do you bleed a lot when drink too much alcohol? Well, 7 months pregnant, his reaction always was, why are you typing in the questions? Why aren't you in the emergency room? So this is something that the system should detect. And, I don't know how useful that is, but Waze has this little thing that says, are you driving or are you a passenger? So probably the system should say, if you are the patient, then run to the emergency room or dial 911. Now, we also need to actually somehow verify and show to the user that the system understood the question. And for that, I think we also, for checking the facts in the answer, we do need to leverage our knowledge sources that we have so that we can confirm the answer with the structured data along with the snippet from the reliable source that we can show. From really good old evidence-based practice, we need to highlight the strength of the evidence in the answer and the system's confidence in the answer, and also explain why the system is giving that answer. So for going back to our drug-drug interaction example, we will need to show that the drug fits the description in the question, that the paraphrased question is kind of conveying the same information, and then show why these drug classes are relevant, and then why the final answer can be trusted. So the tasks we have for tomorrow are still supporting, not really giving, although I know that the users want an answer, but what we really need to do is convince them that they need to think given the evidence that we have provided. And of course, the answers have to be safe, reliable, and care about the user's privacy. The answer reliability, we need to also, the answer can be harmful in different ways to different stakeholders. So we really need to see what answer can be given to, say, if a researcher is looking for some harm or something, that is okay to give them the answer because this is their research question, but it's not okay to give that answer to the consumer. Fact-checking is a very active area of research, but it's still very relevant, or even more relevant now because the current systems are passing all the other tests. They are fluent, the answers look reasonable, but the fact-checking remains their weak point. And value added by the domain knowledge. In the UMLS, for example, do we have enough domain knowledge? What are we lacking? In what form should we provide the knowledge now? And as I mentioned before, the evaluation metrics are still very relevant. So in very many of our experiments, we were trying to show, and probably you all know about that rouge, that measures how far, in terms of the lexical, basically in words, the answer is from some gold standard answer. And we all know that, well, if you use some different words, they will not correspond to the words in the gold standard, but they can still be true. But that metric rouge that we all love to criticize is still very reliable and pretty well aligned with the human judgments of the same answers. So this is what we're going to do for PLABA again. We are going to compare these standard evaluation metrics to the human judgments, see which ones are still aligned. And also, for the manual evaluations, what are the efficient and reliable but not too involved frameworks for the evaluation. So with that, I would like to thank you, and I hope you have questions.
Thank you so much. So if you have questions, please come up to either of the microphones to ask your question. But I'll start it off while people are getting down there. I'm curious, one of your ending comments was about eliciting critical thinking amongst the users of Q&A, and I was wondering what your thoughts are as to how we might want to think about that.
Right. And we're now out of AI and computer science into, I think, behavioral sciences and psychology, and I think this is, because I'm not an expert in that area, right? So I think we have to do more of that interdisciplinary. How do you give an answer so that the user is still engaged, but also somewhat critical and wants to interact further? And there's a lot of, so where we want to go with some of these questions is towards dialogue. Because a lot of these questions is what Dr. Lindbergh used to call follow-up. Even humans reading these questions do not really understand what is the information need behind. Could be this, could be that. So engaging the patient in that way somehow. But also I believe that we need more interdisciplinary research in that area, not just providing the results, but and not even just human-computer interaction, but more of that with the behavioral sciences and social sciences.
Perfect.
Thank you. Fantastic talk. My question is focused on evaluation. So you had mentioned that evaluation, especially in the context of long-form question answering, is really challenging. And I wonder what your thoughts are on the extent to which the large language models can change the paradigm around which we need to think about evaluation, in the sense that they can evaluate themselves, or provide feedback for human annotators to, through active learning and tools like this, to accelerate evaluation in context in these sorts of systems, or or are those techniques kind of too risky because it just risks kind of error cascades? Or I wonder what your thoughts are on that.
That's a really great question. Thank you. The old school says you never use the system that generated the answer to evaluate the answer, because of course I'm perfect, right? I gave you that answer. So, but then I had Yassin Rabet was a postdoc, and he developed, going back to these automated evaluation metrics, he developed a combination of Rouge with a BERT-based model that would, measure the distance using some semantics, not just lexical. And that was back and forth with him but you're using BERT to generate, so how do you use BERT to evaluate? And he somehow convinced me that if that is not the BERT that you use to generate, if that's some other BERT, that's okay. So I think that is the sort of probably towards the answer to your question, where yes, if you use some, not the same language model, not trained exactly, not prompted exactly, that might be a venue for an evaluation.
Thank you.
Great, thank you for the great talk. I was wondering about the role of potentially hybrid systems. So you showed, like in the past, you had these systems which seemed to be accurate, but not great in terms of how they presented the answers and the information. Do you see any way of combining the more kind of newer language models that some of them are really good in summarizing and condensing or presenting otherwise in a more accessible way the information, whether you could combine the two, your more accurate systems, but then on top having some model that transforms that information, that accurate information, into something more digestible?
Yeah, that's exactly what we're trying to do right now. We're trying to analyze the questions with the UMLS still in the picture, but also now use the I wouldn't say large, I would say in our case it's pre-trained, and see if that's better. And so right now we looked at some preliminary results for extracting the focus of the question with a pre-trained model, and it's pretty good. It's around 95. So yeah, there is definitely, I think that's a really good future direction.
Thank you.
Thank you.
Hi. Oh, sorry.
Go ahead.
Oh, sorry.
No, it's okay.
Hi, I have a question. So as an organizer of many of the BioNLP challenges, and having thought about how to evaluate these sort of models, I'm curious how you're thinking in the future about how to evaluate systems that use large language models where we don't necessarily know all the data that they're trained on, and how to think about kind of evaluating those sort of hybrid systems that might leverage GPT-like models in the future.
That's a really great question, and there is a huge concern that we actually don't know what they were trained on. We don't have access to code. I just saw an article that said as soon as the large language models release their code, everything is going to be just great. That's kind of, we are now into some kind of an intelligence. So you don't know what's going up here when I give you the answer. So I think we kind of really need to judge by the result, just by what the system said, not, and that explainability has been an issue for a while now. And we found that the system is really, really bad at explaining itself, and you need some kind of a third-party system to explain why these answers might be okay. And I think the same should go for these large language models. So verification will come from somewhere as an extra, not just, believe me, this is an answer because I was trained on mimic data, but this is an answer because it is supported by this evidence, by this knowledge.
Thank you for your insightful talk. I'm a physician and clinical pharmacologist by training, so I have a question for your drug-drug interaction example. Not every possible combination of two drugs in terms of drug-drug interaction potential has been actually studied. Many of them have to be inferenced based on some kind of rule. So that, I think, can pose some kind of limitations in terms of the generalizability of whatever language model that you would develop. So could you comment on that limitation and then possible ways to get around that?
Yeah, no, that's perfect. That was the sort of the underlying idea for the big mechanism initiative some years ago, where absolutely what you said, we have gaps in knowledge, and it's not everything is stated in text, right? So the idea that DARPA had at the time was that we will generate these answers, which LLMs are really good at generating, given some pathways, some knowledge. So, and this is again one of the, so in a sense, I think LLMs just opened so much new research for us in terms of going forward with, now that we have these bits and pieces of knowledge, structured knowledge, so that will be a multi-modal model. So there is some chemical knowledge somewhere in some databases, there is some language knowledge, there's probably some imaging stuff somewhere, and given all that, generate an answer about the potential interaction. There was a large language model applied to AlphaFold, and it did pretty well. So I think there is definitely a future in that area as well.
Okay, thank you.
Thank you.
We have time for one more question.
Okay. Thank you. So I have a question regarding the when you mentioned the human evaluation. I know we, as an interdisciplinary field, we need to get involved with those domain experts. So we did a lot of human evaluations. So my question is, how we actually ensure the quality of the human evaluation. Because I've read some papers on some like radiology reports summarization or some like those question answering. I saw there's a variations of human evaluations across the, for example, like one time this is like this score, and the next time will be the different performance. So I'm not so sure if you have any experience like promoting the quality of the human evaluation in this case.
Right. So the answer to that, you know, the current traditional answer is multiple annotators, and having the consensus among the annotators and hashing it out. And this is going back to all the way back to the initial 1990-something question answering, where another approach to that is a pyramid. So, you know, you have 9 annotators, 8 of them or 9 of them said this is a good answer, then they agree and this is how much credit your system gets. If only 1 annotator said this is a good answer, then the system does not get that much credit.
Yeah, just a follow-up. So you mentioned like 9 or 6, but in practice for me, like I email many, like for example, like last experience I did, I email many experts. Most of them say they were busy.
Yes.
And I finally I captured 1, and I did. So in the real scenario, how actually to maximize such a confidence in the human evaluation? I know maximum a multiple would be good, but what if?
Actually, so 2 is enough. So for that pyramid stuff, way back when, again, for the original NIST question answering systems, we have shown that 2 is as good as N in terms of relying. Now, if these 2 agree, that's good. And there are these convenience samples where you can maybe recruit a medical librarian that has a little more time. But there is really no answer. It's the same, you know, how do you trust that one LLM? How do you trust that one person? How do you know that one person is not unintentionally? Well, I don't know about you guys, but I've done a ton of annotations, and sometimes you just skip over something. So when you then look at your annotations and someone else's annotations, you go, oh yeah, how could I have missed that, right? But sometimes you kind of go like, no, I'm right, and no, you're wrong, and then you really have to sometimes involve a third party to give you an answer.
Okay, all right, thank you.
Thank you.
So let's thank the speaker again. So our next speaker is Dr. Ben Glocker. Dr. Ben Glocker is a renowned professor in machine learning for imaging and the research chair in safe deployment of medical imaging AI at Chiron Medical Technologies, Royal Academy of Engineering. He co-leads the Biomedical Image Analysis Group, and he heads the ML research at Chiron. Dr. Glocker focuses on the nexus of AI and medical imaging. His pivotal research seeks to develop safe, ethical AI tools to enhance image-based disease detection and diagnosis. With that, I'd like to welcome Dr. Glocker.
Thank you so much for the kind introduction. And it's a real honor and pleasure to be here in the first in-person CHIL conference. So I have the pleasure and was given some time to talk about some of our research. And I guess as a first disclaimer, I should say, so my background is computer science. And I've been working in computing for maybe 15 years, always on the medical imaging side. But what we really saw over the last, I guess, 5, 6, maybe 10 years is that some of those methods that people have been working on more on the computational side have really started to become good and clinically useful. And there are many examples. This is just kind of a random selection of some examples. But we do certainly see AI systems or machine learning-based systems that seem to work reasonably well for disease detection, doing quantification of images, sometimes even discovering new things that we didn't even know that were encoded in images. So I guess with that in mind, and moving more and more towards the question of how can we move that into clinical practice, my research has also expanded from being previously much more focused on the left side algorithm perspective, trying to get algorithms that are more robust, more reliable, working maybe on this systems like failure detection and quality control. But now, increasingly, we have to work at or look at this field from many other perspectives. Of course, there are clinical perspectives, there are societal perspectives. And generally, I think, and that's what we also see in the literature, is that people have moved beyond just reporting test accuracy of these systems, but look at the wider implications. And that is something I want to talk a little bit about today. So my recent research program or agenda, I would say, is very much focused on that or summarized in that diagram. So we, in the past, have very much worked a lot on the AI algorithm itself, trying to increase its robustness and reliability. But now it's starting to think about, once we deploy these AI algorithms, what can we do to make sure that they are safe and reliable in the use in clinical practice. So what can we put around the algorithm itself? So we are starting to think about input and output safeguards. For example, stress testing and quality control I will talk a bit about, but also how can we look at the output of an algorithm. And then, of course, also looking at important aspects of how can we make sure that we can trust these algorithms. So I will first talk a little bit about robustness to make sure that we're all on the same page. I will tell you what my kind of definition of robustness is. You may or may not agree, and we can talk about this, but for me, robustness really concerns the algorithm's ability to preserve its predictive performance under variations in the input data. So the question is whether an algorithm's accuracy, for example, for detecting disease, would be preserved when you move that algorithm between hospitals, use it on different scanners, use it on different devices, maybe even on different patient populations. So one thing that we kind of envision, and many people look into this, is this idea of a neural eye examination. Can we give the AI algorithm to a test, a little bit like when you go to your eye doctor to check your eyesight, to test how the algorithm might respond to changes in the input? And one of those approaches is called stress testing. So here you would take your input data and you would apply possibly or hopefully plausible and maybe expected kind of perturbations or transformations to your input data. For instance, you might change simple image characteristics like the contrast or the brightness, and you want to see how the algorithm reacts in terms of its predictive performance. And one interesting thing that we found in one work where we tried this stress testing approach on a disease detection model for chest X-ray is that it's really revealing in terms of comparisons between different models. So if you look here at the most left side, what you're seeing is the test set performance on an IID test set. And very often that is what you would find in a paper or in an evaluation where someone tells you this is how good the algorithm is on a test set. And on the top we see one algorithm, it's a dense net, it's a convolutional neural network, and on the bottom it's a vision transformer. So these are just two different models. And interestingly, if you hopefully you can see those numbers, but roughly on the very left side, you see that both algorithms have roughly the same test set performance. It's not distinguishable. So there's no statistical difference between the test set performance. However, if you then go from the left to the right and you look at different perturbations that you apply to the inputs, you see very different behavior of those two algorithms or these two models. And in this case, I would argue that the vision transformer on the bottom is much more stable. So it shows a much more stable and robust performance across these different perturbations. And this might indicate that in practice, maybe this is the algorithm you want to deploy because maybe it's more robust to any potential changes in the future. So these type of stress tests can really tell you something about the general, hopefully the generalizability of these algorithms. And so we also applied this to skin lesion classification. And again, in this case, we see that one of the models performs much more stably or much more robust than the other one. And again, you wouldn't be able to see this if you just look at test set performance. Another important issue is because, especially in imaging, so all my work is in the space of imaging, where these days we work with very large data sets. So ideally, when we train a disease detection models, we have maybe tens of thousands, hundreds of thousands, or even millions of images. The problem is you can't really do quality control on these very large data sets in a classical kind of manual way where you go through the images and make sure that you only include, for example, for training, but also for testing, only images that are of sufficient quality. You really don't want to include images with very large artifacts or images where something has just not worked out in terms of the image acquisition. So this is just an example. One of the works we have done with Chiron is where we trained a model to capture the distribution of what the normal kind of expected appearance of the images is. And then you can use a rather simple outlier detection algorithm to very quickly find images which might have artifacts or hardware, or there's something corrupted in the images. And you can do this with data sets that are in the millions, which you really need to do automatic quality control to ensure high quality data. So this is more on the input side. So this is stuff that goes into the algorithm. The images, we want to make sure they are of good quality and that our algorithm is robust. Now the question is, how do we deal with things that come out of the algorithm? How do we look at the predictions, the probabilities of disease presence and so on? How do we make sure that we can put safeguards on those outputs? So this is about reliability, which for me concerns the question whether one can trust the algorithm's output predictions. In particular, it would be great and important if an algorithm could raise a flag, right? Ideally, an algorithm could tell us when it's uncertain and say, on this image or this prediction in particular, I'm not quite certain, you might not want to use this automated prediction. In an ideal case, you then have a way of referring that case, right? Because you, of course, still want to make sure that if you have, for example, a chest X-ray image, that someone makes a diagnosis. So you would maybe refer to a human expert if you had an AI in some sort of automated or triaging system, for example. So this would be the ideal scenario where an algorithm can flag its uncertainty, and then hopefully you have some way of following that up, maybe with a human. Now the issue is, so we looked at failure detection methods. And I think this is where it's interesting, and also I think maybe one of the motivations of having these type of events, bringing people together from different fields and areas and discuss issues that are really real, that have real world impact. And one of the things that we did find is when we tried to come up with some sort of reality check of how good are automatic failure detection methods that are currently presented and reported in the literature, primarily in the machine learning and AI community, often evaluated on kind of benchmark, sometimes a bit more toyish kind of data sets, maybe some computer vision data sets. How well do those work in medical image classification? And the answer is they don't. So unfortunately, so at least on the tests that we run here, so we had 6 medical imaging data sets. We run very different types of models that provide all kinds of different confidence scores that the papers often claim this is the way how you can detect failures of your algorithm. They don't really work. And the best model is still a model that performs well and has a reasonably good calibration of its probability. Then you can use, for example, the softmax output. That was kind of the baseline that almost beat every other presented method in the literature. So there's also a call here. This is a remaining an open research problem. So having ways of doing good failure detection, I believe, is still unsolved. And one of the reasons why this might be the case is if we look at the characteristics of the data. So on the top, it's the 3 data sets that we used, which are a bit more, I guess, on the toy problem side, where it's kind of an MNIST drop-in data set where it's medically inspired, but it's not real medical data. And similar to the computer vision data sets like CFAR10 and all the others, when you sometimes look at the embeddings of the feature spaces of these models, you see very good clustering. You see very distinct clusters of the different classes of those samples. And in these scenarios, failure detection methods and other types of auto-calibration methods and so on work reasonably well. In the medical space, however, it's often much more fuzzy, much more blurry between the classes. So I often say that I think in medical imaging, the inter-class variability is often much lower than the intra-class variability. So you have more variability between individual patients of the same class than 2 patients that having a diagnosis or not. And that is one of the issues why many of those techniques don't translate from applications like traditional computer vision and natural images to medical imaging data sets. Good, so what could we do if we actually had systems that could, for example, automatically detect failures or give us good confidence scores? Or generally, how do we deal with the fact that if we introduce AI into a clinical workflow, that there will be concerns. There will be concerns from doctors, there will be concerns from patients. They do want to know, right? So they want to know whether it was an AI system that looked at the scan or a human expert. And this is an example, again, with Chiron, where we look at breast cancer screening. So in the UK and in many European countries, we use double reading programs, meaning that every scan that is being taken, so this is digital mammography for breast cancer screening, is being looked at by 2 human experts. I know in the US it's primarily single reader, but we can talk about that, how AI could contribute there. But obviously one idea, and that is what many people looked at, is in that case where you already have 2 humans, maybe you can just replace one of them. Maybe you can have the AI system replacing the second reader. In that scenario, you would still always have the assurance that a scan is always being looked at by a human. And screening participants seem to like that. So there was a study in Sweden where they asked women participating in breast cancer screening programs whether they would be happy for AI to be used. And the majority said yes, as long as there's always a human also looking at the scan. So this might work well. However, the question is still, how do you deal with the fact that the AI and the human reader will disagree at some points? And there are many concerns about this from the patient side, but also from the practical point of view. It might be a different type of disagreement because the AI might not exactly operate like a human reader. And there are, for example, concerns that when there's disagreement between 2 human readers, you would refer to arbitration. So there's another panel or an expert or a senior radiologist looking at that scan again. You can do the same, of course, when you just have an AI system and a human reader. But the concern is that you will increase what's called the arbitration rate. So you will add actually a lot of effort on the arbitration process, and people who are in charge and do the policy making and so on don't really like this unknown, because it might actually overburden the workflow and the programs. So sometimes we have to think a little bit clever here. How can we actually make use of the AI? So one thing we looked at is what we called AI as supporting reader, where again we replaced the second reader by AI in the first case. So every scan is being looked at by a human reader and by the AI. And when they disagree, then you refer to a human reader that would anyhow normally be in the program as the second human reader. So in that case, you can assure that whenever a scan is being looked at by an AI and there's a disagreement between AI and a human reader, another human reader will look at this. And interestingly, if you evaluate this, so we had looked at this from in a large retrospective study, is that you still save a lot of workload overall. You preserve the diagnostic screening performance, which is in that paper. You can look that up. And the arbitration rate is very low. So you don't have that same concern as in the middle. You actually have a lower arbitration rate. So that was an interesting way of looking at, okay, so if there's disagreement with AI, you can sometimes in certain situations use human referral. So another thing I want to discuss is the issue of drift detection and auto-calibration. So here's a typical scenario that maybe many of you have faced working with medical images, is that if you train a system on one type of scanner or one type of image characteristics, the performance changes when you test it on a new type of device. Now, in some cases, it's not actually a performance drop. It is a performance change. And that is what we found a lot in the case of breast cancer screening, is that the algorithm was still able to accurately distinguish between malignant and benign cases, or malignant and normal cases. But the performance in terms of the trade-off of sensitivity specificity was completely off, meaning that the threshold that you apply on your prediction doesn't generalize to the new setting. So in that case, what happens is you can look at the output predictions and the distributions, and what you might see is that on the left you have the scanner A, where where maybe you did the evaluation and the testing, and you choose a good operating point that gives you, let's say, an equal sensitivity specificity. If you do that same on scanner B, it doesn't really work, but you can then do recalibration, and you don't need for the recalibration any ground truth data. So we don't need any diagnostic information, we just look at the distribution shift here, and under certain assumptions, which we can discuss, you can do that. And what happens is that if you had a sensitivity specificity that was completely off for the original data set after the alignment, you go back to that equal sensitivity specificity trade-off. And that works really well across different scanners and different scenarios. So often in hospitals, you might have the case where you transition to a new scanner. You bring in a new device from a new manufacturer, a new model, or you might add a new scanner. You might extend your screening capabilities, adding more devices. And in all these cases where if you don't do anything and the model now has to deal with a new type of incoming distribution, your performance will drift. With this algorithm of what we call unsupervised prediction alignment, you can actually recover the expected performance quite well, under the assumption that your overall discriminative performance is preserved. The same works if you have, for instance, image processing updates. So the issue is, as an AI vendor, if you come into the hospital and you deploy your algorithms, and they have to run on different machines, you're sometimes not in control of what happens to the machine. The manufacturer of the machine might deploy a image processing update. They make the images sharper or better looking, maybe even using AI, and that might throw off your disease detection algorithm. The question is, how practical is that approach? And here we looked at how many cases, how many images do you actually need? So on the right side you see how many images or cases do you need until you are able to recover the performance? And it's not a lot, meaning you could run this live. So this is basically after deployment, you look at the distribution outputs, how many cases do you need to detect that there's a shift, and then how many cases do you actually need to calibrate, and it's not a lot. So it is actually a practical approach that in a typical breast cancer screening program, this might mean that you might monitor for a week or two, and then you might decide whether you want to do some updates to your model outputs before you're releasing the predictions of the AI. And a week or two is quite good. So currently in the UK, I think women have to wait sometimes up to a month until they actually get the imaging result. So we wanted to see whether this was specific to mammography. It also works in histopathology. There you might have different staining protocols between different sites. And again, the automatic drift detection and auto-calibration works quite well. And I can share more details if you're interested. So the last thing I want to talk about is how do we do bias and subgroup analysis. So this is really something that we have only really looked at, I guess, over the last 2 years or so. But it is something that has kept us very busy. And I think it is really important. It is really important because there are real concerns, right? So we have probably all seen, and I know some people are here, behind those brilliant works that actually have put this on our research map, right? Saying, look, there's really a concern. There could be a problem if you deploy AI. It might not perform as expected, in particular across all relevant subgroups. And now bringing the two sides, so left and right here. So left is about reported disparities in performance, and the right side is about what is encoded in the images. And if you think about the two together, then obviously there's a concern that since we are always training on historic data, and historic data always is biased, could certain biases being picked up because it is encoded in the images? So the prime example here is that we do now know that race is encoded in many medical scans like chest X-ray, also digital mammography. And on the other hand, what if our data is so biased that the algorithm will pick up a shortcut, a spurious correlation between protective characteristics and disease detection? There is an increasing amount of work trying to look at that problem. And one of the works I think that is really interesting is how do we do auditing? So this goes back to the question, what if someone gives you an AI algorithm and says you can use this for certain types of disease detection problems, how do you make sure that you can check that algorithm, right? So how do you audit that algorithm? So there's some nice work from some of my colleagues who have led that and bringing in this idea of algorithmic auditing also in the medical setting. And one of the key components of an auditing of an audit of an algorithm is subgroup testing. So I want to talk a little bit about the difficulties we find when we try to do subgroup testing. So imagine you do train a disease detection model for chest X-ray disease detection, and you use a large data set publicly available like CheckSpert. But I think it applies to many other data sets, and I think there were some earlier comments about biases in publicly available data sets and how do we check that. Is that if you take CheckSpert and you train a disease detection model for chest X-ray disease detection, you will find subgroup disparities for certain. So if you look at different labels, for example, if you look at the no finding, kind of the ruling out disease label, or pleural effusion, these are just some examples. You can look at all others, you will always find subgroup disparities. And that's concerning. What is more concerning is we don't know exactly why they are there and where do they come from. So in this specific example, so this was a model that we trained, following up from Marcia's work and many others, trying to see, okay, can we reproduce this? And immediately we found yes, you do find a higher false positive rate for no finding, meaning you actually kind of underdiagnose a certain subgroup, and also on pleural effusion, very clear differences in the diagnostic accuracy for some subgroups. So where's that coming from? So this is what we kind of call the algorithmic bias dilemma, is that if we look at the base characteristics of the CheckSpert dataset, for example, but also Mimic, and I'm sure this applies to many others, is that there are already biases in the dataset, right? So the dataset itself is very imbalanced in terms of race distributions. So by the way, here, so every time I talk about race here, so this is taking exactly the population from Judy Gishoya's paper and her colleagues on race detection. And of course, we can talk about like the whole concept. How do you define those subgroups? But if we take those, we see very clear imbalances. So black is underrepresented in CheckSpert, Asian is underrepresented in Mimic, and generally most of the population is white. We also see large differences in age, and that was for me a bit of a question mark. Why is that the case? And again, then if you talk to your clinical collaborators or to people who know a little bit more or much more about this than I do, they do sometimes have some ideas, some answers, maybe some pointers in the literature why this might be the case. But also imagine that, or remember that those type of data sets are very easy to use these days by anyone who doesn't have domain knowledge, like me. So a computer scientist coming in, training an AI system, trying to write a paper with a new idea of how to train a CNN, probably doesn't know about these things. So I don't know why, for instance, black patients are almost 10 years younger in CheckSpert on average. There are also differences in disease prevalence. So for example, you see almost 10% difference in prevalence of pleural effusion for some reason. Again, we don't know exactly why that is the case. Now, one thing that we did try to, so we try to understand why did we see that bias in the disparity? Why did we see performance disparities in one group so strongly? And one idea was, maybe it is really the training set, right? So the training set is biased, you train a model, you see the disparities. What if we change the training set? So I just showed you that CheckSpert and Mimic are actually quite different. They are both biased, but differently biased. But whether I train on CheckSpert on Mimic and I test on CheckSpert, I get the same disparities. So that was kind of interesting, and we weren't quite sure why this is happening. So we thought about, so maybe it is the test set, right? So remember that we have the test set from CheckSpert, so it has the same kind of biases. Maybe it has to do with our test set. But then if it's the test set and the test set is biased, and your model is biased, so how do you deal with that whole situation? How do you know it's the model, it's the training, it's the test? So that is why I call it this algorithmic bias dilemma. So one thing we tried is, and again, this was very naive, so we did test set resampling. We said, okay, we saw in the base characteristics there's imbalance in race, disease prevalence, and age. Let's resample the data to control for that, to remove those imbalances. So we have a resample distribution. Now, this is only done on the test set. We don't touch the training set. Right, so this is what happens. So training on the same data set, but testing on the original and the resample test set, suddenly some of those disparities disappeared. Right, so using this resample test set, some disparities disappeared completely. But not entirely, and not for every label. So for some labels, it kind of disappeared. So if I go now from original test set to resample test set, you do see some differences in AUC, and some of this comes from the resampling with replacement. But the disparities on no finding disappeared. The disparities on pleural effusion got even amplified, or were definitely still there. So that, again, was a bit puzzling. So so with this, kind of, we thought, yeah, there's certainly a problem with the algorithm picking up something, because it's clearly underdiagnosing or misdiagnosing one subgroup. But in another label, it kind of disappears. But maybe the whole test set resampling is also not the right thing to do. And the question is, what do you control for? And sometimes you might know, right? So you might know about your confounding factors and you know what to do. But I think in most cases we don't. Especially if we use publicly available data set, we have very little understanding of what we call the data generating process. And this is where we started a little bit thinking about how can we bring in more kind of causal reasoning into this whole problem. So a couple of years ago, after reading Julia Pearl's Book of Why, which I highly recommend, we started thinking about how can this type of causal thinking impact decisions we make in machine learning for medical imaging. And so we came up with that kind of idea that you really need to start thinking about your data generating process before you do any AI, and maybe then can identify, or at least communicate. Sometimes it doesn't help you in terms of solving anything, but at least you can transparently report on things that you might expect, like certain types of shift. Population shift, prevalence shift, acquisition shift, annotation shift. Annotation shift is one of the worst for machine learning, which is kind of the thing where one subgroup is diagnosed differently than another, so the labels are actually mismatching between groups. Machine learning models cannot really deal with that. But it is important to kind of identify and then communicate the type of shifts you might expect. And of course, we have sample selection bias and so on. So sometimes I think it would help if we try to write out that causal diagram and at least say, these are our assumptions. Okay, so there was a great discussion earlier about large language models and the issue of what do we know about them, what do we know about their training data, and so on. The same, I think, that starts to apply to medical imaging as well. So I still have this open question, foundation models, opportunity or risk. I think many others have the same. And one of the issues is that, yes, on one hand, we do want models that are trained on very heterogeneous, large, representative data sets, and then we use those models as excellent feature extractors and so on. But what about the risks? So could that also actually be something that doesn't quite work as expected? So here we looked at a model that was partially released, I would say. So there's a model developed by Google, which they called a foundation model, chest X-ray foundation model, trained on 800,000 chest X-ray scans, primarily from the US and India. And they made this available as an API, so you could pass your images through and get the feature vectors. But you couldn't get the model, so you couldn't do directly something with the model itself. They didn't release the weights. So we thought, okay, so if that is the setting, like someone produces this beautiful large foundation model saying it's trained on very large heterogeneous data and gives you that model in that form, is that a good thing or a bad thing? So this is the setup, right? So you have a neural network backbone that produces those features, ideally related to disease, and then you try to compare to a model that's trained on Chexpert and a model that is trained by Google in this case. And so we used a kind of a statistical analysis where we looked at the features that were produced by these two models and then did a dimensionality reduction in terms of PCA. So if you do this, ideally the PCA mode should capture obviously the largest variation in the data, which normally should be aligned with disease because your model was trained to do disease. So this is our Chexpert model that we trained on Scratch, and then you can overlay on the PCA modes the different characteristics that you might be interested in. So for example, we see sex and race, and how it relates to the separation of disease. Right, because that's kind of what you want to know. You have a primary task for disease detection, and you have some other characteristics that you ideally do not want to see to be associated with that primary task. And here we see very little differences, I guess. I mean, you do see some shifts, but if we compare this to the chest X-ray foundation model, we saw much more significant shifts in those distributions. Now remember, these are the features. We haven't made any predictions yet. So the question is, does this actually matter? First, in terms of statistics, what we did find, so the first 3 PCA modes, you always see they had a significant difference in terms of no finding and pleural effusion, so they are associated with disease. So let's only focus on the first 3 rows in each table. And then you look at the other kind of pairwise comparisons between subgroups. And what we find is statistically, we find 4 out of 12 and 10 out of 12 tests were significant in the checkspot model and the foundation model. Again, the question is, does it matter? If you look at the performance in terms of, so there's a summary statistic taking TPR and FPR in one metric, all the foundation models actually didn't perform really well on checkspot. But even worse, they seem to amplify disparities between subgroups. So the checkspot model had the disparities already, right? Or we don't know quite where they come from, but the foundation model made it even worse. And I think that is an interesting observation, but also indicates maybe how you can still make use of data sets like checkspot and mimic and so on. Sometimes even if you don't understand exactly where the biases in the data set come from, you can use them for relative comparisons, right? How does it look like for baseline? How does it change when you train something afterwards? So in terms of conclusion and outlook, so definitely the risk of bias is real. It's part of the whole safe deployment approach, obviously, like making those models trustworthy and fair is a key concern and major effort. What we need is comprehensive monitoring. So one idea is that if you deploy AI, you need to build this monitoring framework around it. You want to do image quality control, drift detection, bias detection, all live when you're actually deployed and see live patient data. I do think we need more and better methodology for mitigating bias, a better understanding generally about how does dataset bias affect algorithmic bias, and we need better data sets. I think that's a point that connects to the previous talk. We do need better data sets that we can actually reliably use to test. That is really important. I want to finish with this maybe controversial idea of what if we could generate what if images. Right? Some people are working on this. We are working on this, so this will be presented end of July at ICML, where we looked at deep structural causal models that we embed into deep learning algorithms for image generation. So the idea is that we define a causal diagram. So here we have age, disease, and race and sex, and we say how they are connected. So this is our knowledge bringing in, saying this is how we think there are relationships between these factors, and X is the image that we want to generate. And then can we do things like take an observation and change it, change a certain characteristic of the image. Imagine we could do this plausibly, reliably, and trustworthy. Would that be one way of dealing with biases and our current imperfect data sets? On imperfect data sets, I just want to advertise the Standing Together initiative. So you might want to have a look at this draft standard. So this is a big effort from some colleagues of mine at Birmingham and many people around the world actually coming together and trying to define standards for data diversity, inclusivity, and generalizability for healthcare AI. So please have a look at that. And also, if you're interested in fairness for medical imaging, there's a workshop at MICAI where you might submit a paper the next couple of weeks. So many thanks.
Thank you so much. Just as a reminder, if you have questions, please come up to the 2 speaker microphone stands. But I'll get us started. So you touched on a lot of different things, and there's a lot of discussion about regulatory guidelines for safe deployment. And I'm curious what your thoughts are as to what are the necessary items that we really should think about.
Yes, so the regulatory side is something that I start to get an idea of, but it's not my expertise. I think there are people who know much more about this. If I can do advertising, I would point you to some work by Melissa McCradden, who is looking at this, like for example, from an ethical and legal perspective. I think she just presented a work at the FACT conference on a framework where you both consider ethical and legal considerations together. I think generally in terms of regulatory, where we touch with regulators is, for example, on the whole continual learning aspect. And the data drift example that I showed is, how do you make sure that if you do auto-calibration, that it's safe, right? At the moment, our frameworks don't allow that, right? You're not allowed to make those type of changes. But obviously the FDA, but also the MHRA in the UK, and everyone is talking about how do we deal with that. Because ultimately, I think everyone accepts that the true benefit of AI is if it can continuously learn and improve, right? But how do you deal with that from a regulatory perspective is still a little bit unclear, but I think things are moving there.
Thank you.
Hi there. Question about this notion of safe deployment. You know, as engineering fields mature, we often move from discovering new failure modes to roughly capturing all the different failure modes, and then safe deployment consists of adhering towards best practices to avoid stumbling into each of the known failure modes. Where do you think we are in that journey in deployment in radiology AI? Are in the coming years, do we still have a long ways to go in terms of we're going to uncover novel ways that these algorithms or deployments fail? Or are we pretty far along, and this idea of safe deployment is going to be about doing best practices with failures that we've seen? What's your intuition?
Yeah, so I think with the current approaches, you can go far already, and we do see, I mean, clinical success of AI. Just to give an example, the breast cancer screening tool is being used in hospitals. It's rolled out in the UK currently in a shadow mode, so it's just running in the background. And there are then constant discordance reviews and so on, and looking at what would the AI would have said. In Hungary, they did some tests where they actually used it as an extra reader. So after human readers have done their assessment, and they did find several cancers that were missed. In terms of failure modes, I think we can, and again, that goes back a little bit to the regulatory perspective. If you define your intended use well enough, meaning you have to specify the model, the hardware, the hardware version, the software version of the image generation, I think then you're relatively safe at the moment with those safeguards that you put around. I don't expect completely crazy failure modes from there. But in a more general setting, for example, where you're less in control, where you use these, I would say, AI in the wild, kind of for triaging or screening in rural populations, which haven't been represented very well yet in any like evaluation and training data sets. I think there we are still a little bit in kind of uncharted territory. We don't know yet exactly. I just recently saw, I think the Google Android phone has been updated with a skin lesion kind of recognition system in Google Lens. And people are a little bit worried about that one. Yeah, so I think for certain applications, well-defined applications, we are good. We can use it. We can start using it, especially in systems where we have good kind of safeguards and human referral systems and so on, where a human also looks at it. In others, I'm still, it depends.
Super great talk. It was really enjoyed it. So, and you partly already answered my question, but relating to the kind of recalibration. So you showed an example where you train on one scanner, for instance, and test on another scanner, and you get similar AUCs, but you shift kind of on the curve. How do you think about now doing that for a third scanner where you don't have the ground truth, where you know you can do the calibration, but you don't know if that AUC is still there? Yeah, so there are two things to that. So I don't think that one completely relieves you from doing the still testing with ground truth. So for example, when you deploy in your hospital, you would sometimes do so-called mini retros. So you take the historic data from that hospital, which is hopefully representative of the local data distribution, and you check where you have ground truth. That generally the performance is okay. I think in the future, hopefully we will make progress with what's called performance estimation. I've just saw a beautiful paper from Marcia's group on performance estimation, and a few people looking at that. How do you predict how well your algorithm will work in the absence of ground truth? And I think we're making progress there. But I mean, in high stakes applications, I think you always will have to have some sort of
check with ground truth labels, or at least reviews. So again, in the screening case, what happens with the AI is that even if it runs, you have kind of monthly discordance and concordance reviews. So you look at all the cases one by one, so that there needs to be a group of experts sitting together looking at all the cases where human reader won, AI disagreed. Why did they disagree? Does it make sense? Are there failure modes that are unexpected? But also at the concordance sometimes you want to know, okay, what are the cases where they really agree and where you can maybe even slowly start thinking about, is there a range where you could replace and have AI systems look at the scan first or something?
Thanks.
Thanks for the great talk. So I was wondering, you're talking about deployment safety and mostly accuracy checks. You also said, like, I don't know if you said this, but like using the model as a deployment is sort of like an intervention in the data. The data changes. Doctors use the predictions to make decisions. And whether or not a model is accurate, it doesn't automatically imply that the decision that follows is beneficial for the patient. It might even be harmful. And interestingly, it can be harmful in a way that your model is still accurate. So maybe a model predicts patient group A has a good prognosis, patient group B has a bad prognosis, and then because of your model, the doctors make harmful decisions for patient group B. So you're testing your model, it's still accurate. It's like, oh, great. But how do you protect against that sort of harm?
Yeah, I mean, it's a great question. You can see there I'm still primarily wearing my computer science hat, saying I need to test the system, and that I know, like, metrics. I like to look at metrics. But I know that a lot of people are concerned about this and look exactly at does it actually impact patient outcome? What are the potential harms and so on? That's not my area, but I know that very good people are looking into that, and it needs to be added, right? So I think I should clarify this. What I showed as a diagram isn't that comprehensive. It's still a very narrow view in terms of the algorithmic performance and all the other things like legal and regulatory requirements, looking at potential harm needs to come with that. Yeah, that's my only answer, I guess.
Hi, thank you again, Ben, for the wonderful talk. My question is related to the first two stages you mentioned about the robustness to input and the reliability at the output stage. So you define robustness as like the models, like does the model's behavior change significantly under realistic perturbations of the inputs? And on the output side, you also give an example where the shift or the failure modes detection or the drift detection is due to the real shifts in the data. So suppose that you use your input stage robustness checks to obtain the perfectly robust, maybe causally correct model. Do you think there's still value in the the second stage for reliability, or do you think there's one of them is enough, or do you think there's value to both stages? Can you comment more on that?
Yeah, no, it's a great point. And I mean, eventually, if you get the perfect system, maybe you don't need safeguards. I'm skeptical, right? So this is why in the diagram I tried to say, okay, there's the AI algorithm, and there's already a lot of work on just robustness and reliability. Sometimes they are linked, as you correctly say, or very often they are linked. Whatever you do on that and improving it, I would still think that maybe we should do something on the input and output side and try. It's about the monitoring idea, right? Because eventually these algorithms will be used when you don't have ground truth, right? There is no ground truth once it's in the clinic. Sometimes maybe you get a biopsy result or something. The problem is with everything that you diagnose as not negative will maybe not even be flagged up later on, right? Who knows whether the people develop later disease or the follow-up isn't completely clear. So I think you need mechanisms for in deployment to monitor what's going on. And I think I'm a big fan of coming from that systems approach of saying, let's take as many signals as we can, right? Let's look at the activations in the neural network and see if there are correlations with change in the output drift and so on. Yeah.
Yeah, thank you.
So unfortunately, I think we're sort of out of time, and I apologize to the two folks that want to ask their questions, but Ben will be up here if you want to ask them. I don't want to prevent you guys from going for a coffee break. This is just a reminder, we'll reconvene at 11 o'clock for the oral talks. Thanks so much.
Okay, welcome everyone. I'm Tom Pollard, and welcome to the first session of talks. We have 4 great speakers lined up. Each talk is going to be about 12 minutes, and then we'll try and make time for 1 or 2 questions. So our first speaker is Dr. Li Xu from Hong Kong Polytechnic University. And they'll be talking about pre-training of networks for vision language understanding, and then also announcing a new benchmark data set. Dr. Xu unfortunately couldn't attend, so we have a recorded presentation that I think we can start now.
Hello everyone, my name is Li Xu. It's my great honor to present our paper titled Multi-modal Pre-training for Medical Visual Language Understanding and Generation, an empirical study with a new benchmark. I've been fortunate to be the lead author of this work, and I want to thank my co-authors for their remarkable efforts in making this project a success. We would also like to express our gratitude to the organizers of the CHIL conference for accommodating our online presentations. Unfortunately, due to visa issues, we are unable to attend the conference in person and deliver the presentation. First, I will give a brief introduction to vision languages in artificial intelligence. Vision language aims to learn cross-modal representations for both images and text. It now has a wide range of applications in the real world. There are now several popular vision language tasks, including vision question answering, image captioning, and so on. In the medical domain, there are also several domain-specific vision language tasks, including MedVQA, report generation, and medical image text retrieval. For MedVQA, the input is the image and the question related to the image, and the model needs to give a correct answer. Typically, it is treated as a classification task. As for the medical report generation, the model needs to generate several sentences to describe the image correctly. As for medical image text retrieval, the model needs to give matching scores for all possible image text pairs for ranking and find the best matching pair according to the ranking scores. To learn a better representations for vision language input, vision language pre-training has been a popular way to do this. These pre-training methods are mainly based on BERT or transformer. Pioneering works are VLBERT, Unified VLP, and so on. These models are trained in 2 stages. First, the model is pre-trained with vision language datasets like Microsoft Cocoa, concept caption, SPU, and so on. Generally, the scale of pre-training corpus is larger than 10 million. After pre-training, the model is then fine-tuned onto downstream tasks like VQA and image text retrieval, and so on. As for medical vision language pre-training, currently there are only 3 works: MMBERT, MedView, and ClinicalBERT. All of them have their limitations. Specifically, MMBERT is only pre-trained by Oracle and only for MedVQA. And both MedView and ClinicalBERT are pre-trained by Mimic6R, which is a large dataset with only tracked X-ray images and their reports. So their models may fail to effectively serve downstream vision language tasks involving multiple image modalities or body regions. So there are only limited works for medical vision language training. The possible reasons is a lack of medical vision language datasets and benchmarks. For example, the total pre-training corpus is less than 1 million in the medical domain, which is far less than the general domain. So in this paper, we conduct comprehensive empirical studies on medical vision language training, which can provide insights and baselines for future research. Second, we propose RGC, a radiographic vision language datasets on multiple imaging modalities, which can be for pre-training, and a new benchmark for report generation and image text retrieval. Next is our method. This is the overall architecture of our pre-training framework. Following most previous works, the model is built based on a cross-modal transformer, which proposes a multi-head attention mechanism. Attention marks is also defined in the transformer to control whether one token can attend to other tokens. And our framework also contains a visual encoder and a text encoder. As for the visual encoder, in the general domain, object detectors like fast RCN are widely used. However, These object detectors are not suitable for medical images because there is no such dataset that can help to train a detector and cover most medical image modalities. And there is sometimes no object in the medical images. So we directly compare trainable visual backbones. Specifically, we compare ResNet, Ring Transformers, Moon Transformer, and linear patch. As for text models, we directly apply word-based tokenizer and get learnable embeddings for the text tokens. Following many previous works, we add special tokens in the input sequence. And for pre-training objectives, we apply two widely used tasks, MLM and ITM. Then we fine-tune the model onto the downstream tasks after pre-training. The downstream tasks include MediBQA, representation, and image text retrieval. As for the pre-training objectives, in MLM, a token is randomly replaced by the special token mask. The model needs to predict the mask tokens given unmasked tokens. There are also two subtasks, sequence MLM and bidirectional IMM, based on different attention masks. In ITM, given a image text pair with a probability of 50%, the text will be replaced by another text. The model needs to decide whether the image text pair is matched or not. Next, we will introduce how to fine-tune the model for downstream tasks. For MediBQA, given the input image and question, we use the output of the first special token class to predict the answer. For generation, we directly use sequence MLM as a pre-training as the objective to fine-tune the vision transformer on the training data. And the figure in the middle shows a single step of generation process with the sequence attachment mask. For image text retrieval, we attach a binary classifier with the output of a special token class. We fine-tune the model with the same objective as ITM. During inference, the model predicts the magic scores for all the possible image text pairs in the testing set and find the rank of the ground truth pair to get the results. As for pre-trained data, currently there are 4 large public radiographic vision algorithm datasets that can be potentially used for vision algorithm training, including local, MediCat, Mimic CSR, and IX-ray. However, they all have their limitations as summarized in the table. So we collect RDC from MedPix. MedPix is a website for teaching medical students and physicians. RDC is a small but high-quality medical vision dataset containing over 18,000 cleaning image text pairs. And RDC is also rich in annotations like modality labels, case diagnosis. It can be for both pre-training and downstream tasks like representation and retrieval. However, the raw MedPix data is noisy for pre-training, and we need to clean the dataset based on both images and text. Specifically, we remove captures which are too short or meaningless, and then we remove non-radiology images or images with too many subfigures, and we also clean images with teacher annotations like arrows and words. Finally, we filled out captions containing specific numeric information or comparative descriptions. And here we sample some removed cases. The first one is because the caption contains numeric information and comparative descriptions. And the second one is not for radiology, and the third one is with teaching arrows and words. And tables show the data statistics of RDC. And we further split the dataset on to train set and test set. Note that we do not provide a validation set because the scale RDC is small for a generation task. If we had given a validation set, the distribution between the validation set and test set could have been very different, which may make the validation set not work. Next is our results and findings. Our experiments include the empirical results on pre-trained settings, as well as the results of pre-trained vision transformer on 3 downstream tasks. On pre-trained objectives, from the table, we can find MLM is much more effective than ITM as a pre-trained objective, and ITM may have a negative effect when used with MLM. On pre-trained backbones, we can find that for all of the visual backbones, pre-training on RGC can help to boost the model performance on both MediVQ datasets. We can also find the visual backbones with localities, namely ResNet and Swing Transformer, outperform those without it. And we can also conclude Swing Transformer outperform all other visual backbones on both MediVQ datasets. As for the pre-trained dataset, here is the overall results. And from the table, we can conclude the best pre-trained corpus is a combination of RGC, local, and MedCat. The further use of mimic CSR for pre-training decreases the model performance. And we can find mimic CSR is the least effective for pre-training despite being the largest dataset. And we can also find the vision transformer pre-trained with local can achieve comparable results with those pre-trained with much larger datasets, like MediVQ, MediCat, MXSR, demonstrating its effectiveness. We then fine-tune the best model onto downstream tasks to see the impact of pre-training on downstream tasks. Here is the task and corresponding datasets. From the table, we can find pre-training can improve the model performance on MediVQ tasks to a great extent. And we can find our pre-trained models achieve state-of-the-art results on both MediVQ datasets. And here are the results for report generation. On report generation, we can find the pre-training does not have to improve the performance on generating tasks. We get generating tasks are different and more complicated than classification tasks. It may suggest the limitations of current pre-trained data and strategy for generation tasks. We can also see ResNet and Swing Transformer achieve comparable performance on Mimic CSR and IOX3, but there is a large gap between their performance on RGC. It shows that RGC as a multi-modal dataset might be a better benchmark for report generation than single modality datasets. As for image retrieval, we can find pre-training can greatly improve the model performance on this task. And the Swing Transformer significantly outperform ResNet on retrieval tasks, which is a similar find on previous empirical experiments in MediVQ tasks and repetitive tasks on RGC. And here is the conclusion and the future works. First, we conduct empirical studies to evaluate the performance of vision pre-training models on the various factors, and we further introduce RGC, a medical vision dataset with multiple radiographic imaging modalities, which contains over 18 image caption pairs collected from MedPix. RGC can be used for pre-training as well as a benchmark for evaluating the existing vision models or MediVQ datasets, such as the regeneration and image retrieval. We distilled the experimental results into several key observations, which can be used as a guide to future vision pre-training research. Our pre-trained models achieve competitive results on medical vision tasks, including MediVQA, medical regeneration, and medical image retrieval, establishing strong baselines for future. As for the future work, we plan to explore different ways to build larger medical vision language datasets. For example, we can filter data in an unsupervised or semi-supervised manner. Another direction is to explore multimodal foundation models, such as GPT-4, for medical understanding and generation. In the end, we want to extend our heartfelt gratitude to the MaxPix team, comprising Dr. Demner-Fushman, Mr. Ganyan, and Dr. Smiotopoulos for their invaluable support in our research endeavors and facilitating the hosting of the RGC dataset on the MaxPix website. And here's the reference, and that's all. Thank you.
Okay, so that was pre-recorded, so we're not able to have questions. But I think when I saw this, one question that's always in my head is how we have kind of benchmark data sets that can be made easily available, but also don't kind of encourage overtraining and don't encourage cheating, essentially, on these benchmark data sets. And I know that I think some people here are working on solutions for making benchmark data sets available, and I think we kind of need those solutions. Okay, One of the worst sounds you will ever hear is an English person like me trying to say a French word. And so I'm sorry in advance for saying this, but yeah, I'd like to say welcome to Dr. Vincent Janselm, who is from the Turing Institute in the UK, University of Cambridge. And we'll be talking about improving the way that competing risks are handled in survival models. So welcome. He asked me to call him Vincent and not to say his surname.
So hi, yeah, I'm Vincent, not doctor actually, PhD student still. So today I will speak about neural survival analysis. And so what exactly we'll look at is how to model competing risk in the context of survival analysis. But maybe you're not familiar with exactly what is survival analysis. So I just wanted to do a short introduction of that particular concept. So it's just a time to event modeling. That has the name survival because we are often interested in modeling death. And so we want to know how long this patient, for instance, will survive. And so if we have a predictive variable X, and we just want to predict survival time, and we have all the data, we just can choose a regression model. Here, for instance, this blue curve will be perfectly happy with that, and that will be perfect. The issue that is tackled by survival analysis is the problem of censored patients, because some of the patients that we have won't present the outcome of interest. Again, like if we look into death, but we have a study of only 5 years, some of the patients will die, some others won't. But we know that in the whole population, everyone will actually die. So how do we actually model those patients? That's the main question that is trying to be answered by survival analysis again. So if we were just ignoring them, that will be terribly biased. So the way of doing that is by maximizing the likelihood of what is observed. So that means that for the patients that are censored, we know they have survived above a certain time horizon. And that's what the survival function trying to model is what is the probability, given my covariates, that I will survive above a certain time. So that's the standard kind of survival analysis. We have some patients that enter the hospital. Some of them will have the outcomes that we are interested in. In our study, we'll look mainly at cardiovascular disease, but some of the patients will be censored by the end of the study. We just choose a survival model, we feed that, and we have like the probability of modeling cardiovascular disease given time. That's perfect. We can use a risk score and then indicate which treatment a particular patient should use from that. The issue in medical data is that we might have other outcome that happens during the study period. So here, this last patient on the bottom of the slide just died before the end of the study, did not observe the cardiovascular event, but death might be correlated with the outcomes that we are interested in. So how do we take into account that particular outcome? That's what is a competing risk. That's a risk that precludes the outcomes that we were actually interested in. And so right now in survival analysis, what is done is usually consider those patients as if they were censored, despite the correlation between their outcome and what we are interested in. So if we were doing that, we would obtain this first curve here on the right. But if we actually account, we'll have a really different survival probability predicted. And that have really consequential impact on medical practice. I will present that later in the slides. So how can we model actually competing risk? That's the main question we try to answer in our work. So I will just start by making a short overview of what is done in statistics and then explain how that has been extended so far with neural networks. So just a short reminder, survival analysis is really trying to model this function S, which is the probability of surviving above a certain time. But equivalently, we can model those two notation. I'm sorry to introduce those other notation, but usually it's the ones that are targeted in the standard statistics, which are known as the end hazard and cumulative hazard. The Cox model exactly that hazard as a baseline hazard multiplied by a covariate drift. So again, if we think about a regression, the baseline is just the mean, and we just try to compute how the different covariates will shift us around this mean. The problem with this model is that it does not take competing risk into account at all. Because when we are interested in competing risk, we want to model this quantity, which is a joint probability of observing that particular risk and surviving above a certain time horizon. So we can do that by just estimating these huge integrals that we have in this bottom slide. where the lambda could be estimated, again, using different Cox regression. The issue with that is that each Cox model will ignore the other outcome. And so that's suboptimal because it's kind of a two-step process instead of jointly modeling the two outcomes of interest. Fine gray is a model that has been proposed quite a long time ago now, but this huge probability is just showing that they try to model that in parallel, jointly the two risks into account by modeling the sub-distribution hazard. And that's the main inspiration of our work, is to try to model both outcomes at the same time using a neural network. What has been done in the literature with neural networks is three main ideas. The first one is discretization of the survival function. So instead of just modeling the survival distribution, we'll just split it into smaller time intervals and then try to use a neural network to learn those probability for those small time intervals. By doing that, we have an approximation of the survival function that might be quite expensive to compute if we want a really fine estimation of the survival function. Another way of doing that, again, an approximation of the survival function, is doing a parametric assumption. And so what that deep survival machine has done is just parameterizing different variables through neural networks. But again, that's an approximation of the survival function. The final one, the closest to our work, is this serve that try to model the derivative of the cumulative incidence function, the main quantity that I introduced at the start, and then solve an ODE to actually estimate the function f that we are interested in. By doing that, again, they approximate the cumulative incidence function because they need to solve this integration in the ordinary differential equation. And so what we propose is quite simple, is instead of modeling the derivative of f, why don't we just model the f directly and obtain the derivative by backpropagation through the neural network? And by doing that, we have the exact likelihood, the exact cumulative incidence function, so no longer any approximation, but in addition, we are much more computationally efficient because we do not need to approximate an integration that will require multiple paths through the neural network. So how do we do that exactly? That's the proposed methodology, which is the neural fine gray. So that's really just three simple neural networks. The first one, E, will embed the data that we have. And then we'll go through two different neural networks, a balancing one that will try to say, what is the probability for that covariate to present that particular risk? And then the second one, which is, I think, the most interesting part, is a monotonic neural network that will try to model the probability distribution of surviving above a certain time, t, knowing that there will be for that particular risk. So maybe you're not familiar with what a monotonic neural network is. So that's simply a neural network. If you add any positive quantity to the input, you expect the output to be larger than if you were not adding this quantity. So here, like mathematically, that just like the output is larger than the one is if we did not add any time dimension. How can we do that? So if we just remind us what a simple neural network is just like a weight matrix plus a bias, and a really simple way of enforcing monotonicity without any kind of really complex optimization process is to enforce all the weight to be positive. So what we do is just taking the square of all the parameters in the neural network for the weight, and we backpropagate as usual for like training. And by doing that, we are totally sure that the outcome of the neural network will be monotonic in the time dimension that we are interested in. And so that's a really kind of efficient way of doing that. But also, it's proven that it's a universal monotonic approximator, so we do not lose any flexibility to model the survival outcomes that we are interested in. So great, we have a model that seems to be quite efficient, but what is the actual impact on medical practice? So what we looked into is cardiovascular risk, and particularly the Framingham data set. We have around 4,000 patients, 18 covariates at the time of entry to the study, and we try to model what is the risk for that particular patient to have a cardiovascular event in the next 10 years, for instance. In this study, the majority actually were censored. We have 26% only that had a cardiovascular event, and some of the patients died. And so we really wanted to take into account death in this predictive model. The way we did evaluate that is just doing a 5-fold validation, and we used two metrics, which are the C-index and Brier score, evaluated at different time horizon. But those metrics are just survival equivalent of the AUC and the Brier score that you're kind of usually using in any kind of evaluation. So this huge table is just measuring those two different metrics at 3 different time horizons. What I really want to just say from this slide is that we performed at least as good as the state of the art. But in the paper, you can also see that we do that much faster. We have a n/2 computational gain compared to the best methods that exist. So it's much faster to train, much faster to predict, and we performed as well. So that's like great. We performed quite well on the task that is interesting, but is it actually important to model this competing risk? And so what we propose here is just doing the models that take into account the competing risk and the ones that do not. And what we see is that we improve a lot. We improve at least a little, the predictive performances. That's, yeah. So it's quite important if we want a good predictive model to take those competing risks into account. But more importantly, when we look at which group benefits the most, when we compare those two predictions between those two models, what we can compute is the difference in the Brier score here and see that more the value is negative, more the patient would benefit from using the competing risk. And what we see here is that the oldest group, which is also the one that is the most likely to actually die, will benefit the most. It's really important because that's also on those patients that we will compute this risk score. So we actually want to be the most accurate on that population. And so it's really crucial to take into account the competing risk. So I'm sure that here you certainly know someone that has been recommended to use a cholesterol-lowering drug. Usually a patient goes to the hospital, there is a blood test that has been done on that patient. We compute a risk score from this particular blood test that tells us what is the risk of developing cardiovascular disease in the next 10 years. If we do that, in the UK, usually we say that if you have a risk over 10%, we would recommend you to use this drug. Otherwise, we'll just wait until the next year or the next visit to the hospital. Here, I just show quite schematically, if we were computing like the two different risk score, one that take into account and one that doesn't take into account the competing risk, we would have totally opposite recommendation. For for cholesterol-lowering drug, that might not be a big issue because there is not that many side effects. But if we think about cancer, maybe, or like other much more side effect drugs, that might be much more important. And so the main conclusion of this work is really, do you have, in your data, some kind of competing risk that might preclude the outcomes that you are interested to model? Because it's really crucial to model them to have accurate but also useful medically models. Thank you. If you want to have a further read on the paper, you're more than happy to look at that.
Thank you, Vincent. I think the paper and the presentation give a really convincing kind of argument that we should be getting better at accounting for competing risks in survival models. Do we have any questions? Please come to the front if you have questions. Ben?
Yes, hi, thanks. Thanks for the nice presentation. Just a quick one. I'm not familiar with survival analysis, but just for my own understanding. So on the bottom one, the competing risks, do you need to take into account the cause of the death? So, I mean, you could imagine that let's say you look at cardiovascular disease, but someone has a car accident and dies. That doesn't really relate to the risk of cardiovascular disease, right? So
yeah. No, totally. So I think that also a really good point is what is the granularity of data you have, because it's really important to model any competing risk that is correlated with the outcome of interest. But again, car crash, for instance, we could consider that as censoring, and that will be fine because it's totally independent of the outcome of interest.
You do take the correlation into account between?
Yes, only the ones that have like the correlation. Yeah.
Thank you. Any more questions?
Hi, thank you. That was a great talk. I'm a biostatistician by training, so I'm happy to see a survival analysis presentation here. So my question is, I'm also studying computer science on a part-time basis, so I sometimes see different practices in terms of how to treat, time to event outcomes. So I sometimes see people do like they would exclude patients with without any event and with shorter follow-up, and then they would turn into a logistic regression model or like a binary that's treated as like a binary outcome. So do you see, compared to survival analysis, do you see any problem in doing that? And then the second question is, Ben just talk about a lot of great deployment with medical images, and I'm wondering if your proposed method would work with images in sort of predicting cancer risk or cardiovascular disease risk, stuff like that. Thank you.
Thank you for the question. So that's the advantage, I would say, of neural networks is that you could use it with any kind of data. You would just need to replace the embedding neural network, like that was the first part. So yes, that will be actually something really interesting to try to model what is the risk of having another event of cancer, for instance, as a survival analysis. I think it will be really good. And on the second question about ignoring patients that do not have the outcome of interest, I would say that's really biased in the sense that it's a missing not at random kind of problem in which we would just do a complete case analysis. So I think, again, that's just like ignoring some of the information that we have access to and that we should, I think, take into account.
And I think just before your talk, Vincent had said that he was inspired by Ben's talk to do something around images. And you both live in Cambridge, so you should try and meet up. Thanks, Vincent. Okay, so our next speaker is Eunbyo Cho, who's from the Korean Institute of Science and Technology. And she'll be talking about use of CNNs for encoding EHR data. So welcome.
Hi, everyone. I'm Eunbyo Cho, a master's student from KAIST, and it's my pleasure to introduce our paper, Rediscovery of CNN's Versatility for Text-Based Encoding of Raw Electronic Health Records. Before diving into our research, let's begin with a brief overview of electronic health records, EHRs. EHR is a comprehensive database that stores every medical event that happens to a patient. In each table, each row corresponds to a single event, and columns represent the feature variables. Since EHR is time series data, patient medical history can be represented as a sequence of events. With growth of EHRs, there are large potential to predict clinical outcomes, synthesize EHR, and gain medical important knowledge. However, EHR systems is heterogeneous. This is because each hospital adopts their own database schema, a code system, and manually selected features for clinical tasks. Consequently, the trained model cannot be shared across easily shared across the hospitals. To address this, recent work introduced the framework called UniHPF, which exploits the universal texture embedding method. It utilizes the code descriptions instead of codes itself, and embed all features instead of manually selected features. Which makes this makes it shareable across the hospitals without no performance loss. On the technical side, converting tables into text from all columns allow us easy embedding with minimal preprocessing. However, it also makes the input size much larger, posing computational challenges for learning efficient representation for clinical tasks. For example, when we consider only 3 events, lab input events and prescriptions, within 12 hours of first ICU admission, the resulting token exceeds 8,000 tokens. Therefore, we propose a versatile encoder that reduces the large data into a manageable size while preserving the core information to perform diverse clinical tasks. To verify the encoder, we experiment on reconstruction, prediction, and generation using our proposed encoder. This figure provides a glimpse into the core of our research. Let's start with the input X. X is the linearized table. In the table, we can leverage the inherent hierarchical nature of EHR, where the event is located in the upper level and feature is located the lower level. When we represent events as table name, column name, contents, column name, contents, and so on, the X hierarchy curve reflects the hierarchy of EHR with fixed size through truncation and padding. While X flatten represents the flattened hierarchy by concatenating events after removing pad from the middle of X hierarchy curve. Now, I will explain encoder design, which includes hierarchical structure and flattened structure. Starting with hierarchical encoder, it consists of two stages encoder, text encoder and event encoder. First, X hierarchical is embedded to E hierarchical with embedding dimension D. And each description embedding is fed to text encoder, flattened and concatenated along the event axis to produce Z prime. And finally, Z prime is fed into the event encoder to produce Z, which is a latent vector. On the other side, in the flattened structure, X flattened is embedded into E flattened and fed to the text encoder to produce Z. It is important to note that text encoder and event encoder share the same encoding strategy. So we can generalize the input and output for each encoder to explain how EHR is compressed to the desired dimension. For CNN-based encoder, each layer reduces one or both dimension into half at a time. And transformer-based encoder reduces the channel dimension into half or leaves them unchanged at each layer. And it reduces temporal dimension using adaptive average pooling at the end. For details, please refer to the appendix in our paper. Let's move on to the experiments. We use publicly available Mimic3 and EICU. Our investigation focused on exploration of encoder with different structure and different backbone for 3 downstream tasks: reconstruction, prediction, and generation. We also investigate the varying compression rate, ranging from about 1,000 to 10,000. Let's move on to the task definition. For reconstruction, we use encoder and decoder and evaluated the model by using token level accuracy. And for prediction task, we predict 6 clinical outcomes, including diagnosis, final acuity, mortality, and we evaluated the models by AURC. For generation, we unconditionally generate raw EHR using VQV approach, and we evaluated the model using 3 metrics. First is we propose a metric to measure preservation of table syntax and semantic consistency. In here, semantic consistency is, for example, columns related to lab tests should appear in lab tables, not prescription table. RC is defined as ratio of correct events to total events, and ratio of correct samples to total sample is denoted as RCS. And also we evaluated the generative model using t-SNE visualization and privacy evaluation. Now let's see the result. The color of the bar represents the structure of encoder. Blue one is for hierarchical and the red one is for flattened. And the group of each group of bars indicates the specific combination of encoder and decoder backbones. For example, T-C represents the transformer encoder and CNN decoder for reconstruction. We compare the model with different encoder but same decoder, and vice versa for the decoder. And in conclusion, CNN outperforms transformers when used as both the encoder and a decoder. For a prediction task, regardless of the backbone models, hierarchical models show superior performance than flattened structure. And in the hierarchical setting, CNN-based encoder shows comparable for performance to the transformer-based encoder. For generation task, CNN-based encoder, decoder, and decoder score high RC and RCS, which means they have ability to maintain table syntax and semantic consistency across all data sets and latent dimension. And also, the latent distribution encoded by CNN-based encoder shows a more similar distribution of original data. On the other hand, the distribution encoded by transformer-based encoder shows some clusters that contain not original data, which is circled by green. Throughout all experiments, models with hierarchical structure consistently outperform the models with flattened. These findings implies a value of leveraging the inherent hierarchy in EHR. Lastly, in terms of time and parameter efficiency, hierarchical CNN encoder shows better performance with lower computational cost. In all figure, the CNN hierarchical encoder, which is blue dots, are located in the upper left part of all figures, where x-axis are training time, flops, and number of parameters, and y-axis represent performance. So in conclusion, CNN-based encoder with hierarchical structure is versatile. It reduces the large row EHR into a manageable size, but also preserves patient's core information to perform diverse clinical tasks. It outperformed the state-of-the-art model on widely accepted tasks in this field, even with fewer parameters and less training time. And we also found that making use of inherent hierarchy of EHR system can boost the model performance. Thank you.
Thank you. Any questions? I think one interesting thing for me is there's lots of effort going into harmonizing EHR data. We are trying to put MIMIC, Boston Hospital data into the same structure as data in Seoul National Hospital. And do you think that those efforts, you serialized your data beforehand. Do you think that we're kind of should be spending our efforts on improving the way we do modeling so that it's able to handle different structures of data, or do you think those harmonization efforts are important?
I think harmonization is important in this field, EHR field, but this requires so much effort or manual pre-processing. So if this approach is possible, I think we may put efforts, less put effort. Yeah.
On the harmonization.
Yeah.
Yeah. It would be nice if we could spend less time harmonizing, because I think it's very difficult to do well.
Yeah.
Question.
Could you go back to the slides of the how do you actually compose your hierarchical and flattened data? I believe it's the first few slides. It was the sizes of the data. Sizes of the a little bit more. A little bit more. Okay, right here. No. Next one. Yeah, right here. So I noticed you concatenate the data for the flattened encoder. So what is the sizes of this concatenated sentences documents?
For example, X hierarchical.
I noticed that was actually up to 10,000 words for this single entry, right?
Yeah, X flatten is 8,192 tokens.
Sorry, I'm not hearing.
8,000 tokens.
8,000
Yeah.
And can you text encoder to encode all the 8,000 tokens?
Yeah, of course.
But usually text encoder is like transformer, like BERT. They only takes 500 tokens.
Okay, I see.
So how did you actually process those your text encoder encode all these long sentences?
For X flattened, we use performer, which is the efficient transformer of transformer. So yeah, we can handle this length of X flattened.
Okay,
yeah.
Thank you. I just want to clarify this because.
Yeah, we use performer. Yeah.
All right, sure. Thank you.
Thank you. Thank you again. Thanks. Do we have a Dr. William LaCava in the house? Okay, yeah. Welcome to Dr. LaCava, who will be talking. Who's from Boston Children's Hospital, Harvard Medical School, and we'll be talking about how to make risk models fairer.
Is that better? Okay. Hello, everybody. I know I'm standing between you and lunch, so I'll try to be fast. Okay, once the rockets are up, who cares where they come down? That's not my department, says Werner von Braun. Who's familiar with this Tom Lehrer song or quote? Okay, he was a kind of a satirical songwriter, and this quote is usually used to, poke fun at the fact that scientists historically don't necessarily care about the downstream outcomes of what they do. But I think it's still relevant when we think about fair machine learning, even when we want to put fairness into the world. This question actually was raised a little bit earlier today, but the kind of broad question I'm interested in is how do we know that a model will be used fairly? So if you're like me, you're mostly concerned with kind of the modeling workflow part of this diagram, where we want to do a really good job of taking EHR data, doing the machine learning pipeline in a good way to validate models, and then once the model is deployed, it kind of goes over the fence to a clinical team. But there's a ton of machinery on that side between the care team, the patients, the payers, the hospital, that produce patient outcomes that don't necessarily reflect the type of fair machine learning metrics that we've validated for. So what can we do to kind of try to make fair machine learning care about the other side a little bit more? We don't really know that a model is going to be used fairly, I think. But there is some stuff we can do to limit what can be learned by decision makers when they're using a model. And that's what we explored in this paper. So just to give an overview with fair machine learning, there's kind of two steps. So first, we want to define some measure of fairness. And for group measures, we're focused on having an outcome, our risk predictions from a model, and a subpopulation or group, G. And then we're going to use an algorithm to try to optimize a model to satisfy that metric. What we argue in the paper, and I think is true, is that sufficiency, one fairness notion, is one that's almost always appropriate in the medical contexts that we study. And the idea here is we want the outcome to be independent of group membership conditioned on the risk prediction. So if the model gives you a risk prediction of 0.7, the outcome for a patient shouldn't at that point depend on their group membership in some way. And it's a fairness notion that's underlying things like fair calibration, or fairness in positive predictive value, for example. What is fair calibration? Well, this is the idea that the model is calibrated well for every group. Calibration is the situation when we have a model that predicts a risk of R, and when we look at patients that get that risk prediction, approximately a fraction R of them actually have the outcome. This is a general kind of good model in a lot of situations. Fair calibration just says that that should also hold for all of the groups that we're interested in. Why do we want it? Well, if we have a model that's fairly calibrated, then we can prioritize patient care. If we don't, we risk having some groups get systematically deprioritized by the hospital system based on the decisions made on this model. Kind of a famous example by Obermeyer et al. In this 2019 paper looked at an algorithm and showed that at a given risk score of that algorithm, black patients were considerably sicker than white patients, which could result in those black patients essentially getting care at a later stage than they should be. So that's, I'm going to skip a couple slides, but that's kind of the basic motivation. So what can we do about it? Multi-calibration is one method and a measure that tries to fix calibration of models in a post-processing step. A model is alpha multi-calibrated if its predictions are within alpha of the true risk for all the groups. So if we have a calibration plot here, we have our predicted risk on the x-axis, we have the kind of measured population risk on the y-axis. For all of the groups, we want the measured population risk to be within alpha of what our predicted risk is. Okay. So does this satisfy sufficiency is something we investigated in our paper. And the way that we did that is to try to come up with a measure that was a little bit more closely tied to the definition itself. So one way of expressing sufficiency is as a differential. So imagine you have two groups, A and B. If you have a model that satisfies sufficiency, then the probability of the outcome conditioned on any risk score and group membership between the differential between two groups should be 1 if you look at any pair of groups. We can make an approximate version of that, which we call differential calibration. So named because we're looking at differentials in the outcome conditioned on the risk score between groups. And we're just measuring that using this value epsilon. And if you're familiar with differential privacy, you'll probably see that this looks a lot like that. And it's true. It does have a relation to differential privacy, or more specifically, pufferfish privacy, in that we get this associated privacy guarantee. It's a little bit different to interpret it because here we're not really concerned with protecting patient privacy, but we get what I would refer to as kind of equity and trustworthiness in the model, right? So if this measure epsilon is going to tell us kind of how much information about the group is relevant to the outcome after we look at a risk score. And this can be used to kind of infer, how much a model can learn, how much a decision maker can learn to trust or distrust a model for certain groups, which we want to prevent from happening. So if we look at multi-calibration under this metric, what we can see is that when subpopulations have different risk profiles, a multi-calibrated model can have a larger % error for some groups rather than others. And this can prevent multi-calibration from satisfying sufficiency. So we proposed a pretty simple tweak to the definition of multi-calibration that we call proportional multi-calibration, because instead of looking at just the absolute difference between the risk and the measured population risk, we're going to look at it as a fraction. So a model is alpha proportionally multi-calibrated if its predictions are within an alpha fraction of the true risk for all groups. And the way that this is reflected as a constraint is just to kind of have the constraint narrow for as the kind of the predicted risk decreases. We did a simulation study to kind of, show that for even the same value of multi-calibration, you can have very different values of proportional multi-calibration and different values of differential calibration. But just to kind of summarize some of the problems that we are looking at with multi-calibration, decision makers may be able to detect differences in calibration between groups, even if a model is multi-calibrated, and this might lead to the model being less trustworthy for some patient groups rather than others. And with proportional multi-calibration, we're kind of decreasing the dependence on the outcome rates between groups being different. We show that it still satisfies multi-calibration, and that it approximately satisfies this measure of sufficiency that we came up with called differential calibration. And we argue that that is kind of a way of ensuring that a model is going to be equally trustworthy for a decision maker. So how do these measures get satisfied? There's a post-processing algorithm that Iber Johnson et al., who did the original multi-calibration paper, came up with. And we just do a little modification to it to make it work with proportional multi-calibration. But essentially, if you have any model from any machine learning method that has risk predictions, and you have some validation data, you can post-process your model to try to satisfy this. So we did that for predicting patient placement in the emergency department. We have a model called POP that is used at Boston Children's Hospital to try to expedite patient visits when you show up to the hospital, to the emergency department and get your vitals taken. It's going to make a prediction of whether you're likely to be admitted or not. And then that prediction will be used to coordinate a bed before that admission decision is actually made. So it works pretty well. It's been validated in some papers by my colleagues in different hospital systems. And we reproduced this model using Mimic4ED, which is a nice open source data set from Beth Israel covering 8 years of admissions data there. Just a quick summary of the results. I'll be around if you want to talk about them more, but what we see with most of these multi-calibration methods, including ours, is a pretty small difference in AUROC for models. So we're looking at basically random forest, logistic regression, and deep neural nets trained on this data. When we post-process for multi-calibration, which is MC boost, or with PMC boost, which is proportional multi-calibration, the AUROC is about the same. Multi-calibration loss gets a little bit better for random forest and DNNs that tend to be more miscalibrated. But at the same time, we get a much better proportional multi-calibration loss and differential calibration loss when we post-process using the method that we are proposing here. So we looked at this for specific subgroups in the data. We were subgrouping based on ethno-racial identity, insurance, and gender. And we can see for some example subgroups that we are actually able to improve the calibration curves, which is nice. So just to conclude, fair calibration, it's one of the most useful ways to improve the fairness of risk prediction models, or perhaps one of the lowest hanging fruit. And proportional multi-calibration is an approach to fair calibration that controls the fraction of calibration error that's experienced by each group rather than the absolute value. And this allows us to connect it to differential fairness and differential privacy to get a guarantee that a model is, in some sense, equally trustworthy for different groups. So we're trying to incorporate this differential fairness approach into other fairness notions and looking at applications across different hospital sites, as well as the real-time monitoring scenario in our future work. So happy to talk about all of that. Thank you.
I love the quote you had up at the beginning, and I think probably answers the question I had, but how often do you see people paying attention to kind of subgroup calibration in machine learning papers that you read now? Pretty.
I see it, but it's usually people who are working on fairness. I don't think it's worked its way into kind of the general machine learning audience.
Yeah.
Yeah.
How can we kind of encourage the machine learning community to think about calibration, in subgroups when they're doing their work?
Yeah, good question. I think there was a nice slide in one of the morning presentations showing some different proposals for auditing that I would love to see standardized and kind of expected. I'm not sure if the best way of doing that is to have it be a requirement for a submission, or if it's to drum up enough support that it's just what's expected through reviews. But yeah, it's a good question. I'm not sure.
Any more questions?
Sorry, just a quick one to clarify. So when you do subgroup-specific calibration, does it mean that the subgroup membership is part of the input to the risk prediction model?
It can be, or it can't be. We don't really
What if you
distinguish.
don't? Do you need to kind of have a proxy, or do you need to predict it along?
So when you're doing post-processing, you need to have that information, but it doesn't necessarily have to be in the model. You're basically training like a set of nudges on the back end that are based on group membership, but the model that you're adjusting doesn't necessarily have to be a function of the group inputs. Ultimately, the total model is going to be a function of the group inputs after post-processing, but it doesn't require it for the base model.
Okay. And maybe one follow-up question. So at the moment, this is a one-off kind of calibration step that you do once as a post-processing. Could you imagine that to use kind of as a continual kind of recalibration, like once it's deployed and you do some kind of online recalibration? Does that make sense in that?
Yeah, totally. That's where we're trying to head. There's been some work with multi-calibration to look at it in online settings, and it's certainly, it seems possible. There's some question of how it's done, because at the moment it requires some randomness in the way that you nudge the model that might not, that's not ideal for patient settings when you're making individual level decisions, but yeah, definitely.
Okay, thank you, William. Thank you to all the speakers in this session. Thank you. I have a few things to say. I need to remember what those are. I think, so we have 1 hour for lunch. Lunch is not provided, but apparently we have a slide here with lunchtime recommendations. I don't see it. Back?
Other way.
Forwards or back?
Back.
Sorry. Okay, sorry, this is the lunchtime places. If you want any recommendations, then come down to the front and we can give you more detail. So you have an hour for lunch. After that, there will be a keynote by Dr. Cheng, a scientist at DeepMind, talking about machine learning for genomics. You've seen the first few slides. If you're giving a presentation this afternoon, please make sure that you've come down and introduced yourself and checked your slides. You can do that now. That would be great. Is there anything I've missed? I think that's it. We're done, and look forward to seeing you in an hour. Thank you.
As people trickle in, I'll make a few announcements. So good afternoon, everyone. I hope you are all energized after the lunch. Before we get to the talk by Dr. Cheng, I'd like to make a few announcements. So firstly, someone left a phone inside the auditorium. So if you are that person, go see the front desk. Then if you registered for the reception at the end of today, you'll see a ticket at the back of your badges. If you don't have that and you registered, please also see the front desk. If you want to reserve a ticket for the social tomorrow, again, see the front desk. And lastly, if you are a poster presenter and you need push pins to pin your posters, they are available at the desk. And lastly, remember our hashtag CHIL2023 if you are a Twitter savvy person. Okay, with that, I'd like to introduce Dr. Jun Cheng from DeepMind. Dr. Jun Cheng is a senior research scientist at DeepMind, specializing in machine learning for understanding genetic code and disease mechanisms. Previously, a scientist at NEC Lab Europe, he contributed to work on personalized cancer vaccines. With a PhD in computational biology from the Technical University of Munich, Dr. Cheng's influential work has been featured in esteemed publications like Genome Biology, Bioinformatics, and Nature Biotechnology. With that, please help me welcome Dr. Jun Cheng.
Okay, that's better. We're over lunch break now, so next slide. Thanks for being here and thanks for having me here. Today I'm going to talk about something about how do we model biological sequences and also how we apply those models in research and applications. I realize that we have actually very broad audience here. Therefore, the talk will be more on the broad message, not too much into the technical details. However, if you do interested in, feel free to talk with me. So we all know that our genetic information is encoded in the genome, and the genome has roughly 3 billion base pair letters of ATGC, and only roughly 1 to 2% of them are actually encoding for proteins. And the genetic information flow from DNA to RNA through transcription. And then this RNA will then translate it into protein sequences, which eventually fold into functional proteins. This is very simple central dogma. However, the genome is far more complex than that. So in fact, we're far beyond understanding the complexity of the genome. As this famous phrase from Eric Lander after finishing the human genome sequencing project said that the genome, we bought the book, but hard to read, since there's so much going on and we're very far. So luckily, with the time involved, the cost of the sequencing has dropped dramatically, actually way better than Moore's law. At the moment, we are approaching like $100 per genome, which is, we can't imagine that like 20 years ago. With this sequencing cost drop, we have generated a huge amount of sequencing data. But now the question is, how do we properly model these sequencing data and how do we make use of them to understand the genome and hopefully interpret them? There, broadly speaking, we have two types of sequences we mainly deal with. The first one is DNA or RNA sequence, which has 4 alphabets, ATGC, very simple. And then the second type is protein sequence, which has 20 alphabets, slightly more complex, but 20 alphabets corresponding to the 20 most common amino acid. So with those sequences, and we want to build models on those sequences, hopefully model the complexity well. And then with those models, what we typically want to do, and I want to highlight here, is 2 specific applications. The first one is to understand variance, is to predict variant effect, where there are mutations in the genome. What does that mean? Is that good or bad? And the second one is on representation learning. So we can train now very large scale models in an unsupervised way? Can we make use of those models in downstream applications so that we can be the downstream application can work better and leverage on the pre-trained large models? Variant effect prediction. So a huge amount of effort in genomics is really try to understand, what's the genetic code, and this is currently a very much unsolved problem, but vital in genomics. For instance, what does variant effect prediction mean? Is that, say, we have a mutation here in the genome, for example here, a T converted into a G as a mutation. With the model, we try to understand questions like, does this mutation change gene expression transcription, or does this mutation affect RNA processing, or does it affect protein function if it happens in the protein coding region? And eventually, with that model, we want to understand or predict, hopefully, that does that mutation eventually increase the disease risk or decrease the disease risk? Does that related to disease at all? And with the models built on, or deep learning models built on DNA sequence or RNA sequence, there are roughly two types. One is we build a model on the DNA sequence, and we try to model, gene expression directly from the sequence. Because in theory, all the genetic information are already encoded in the sequence itself. So with a powerful model, properly model the sequence, we should be able to predict gene expression. The same as if we have a proper model on the protein sequence, we should be able to predict the folding problem. That's the gene expression. And we can also have models focusing on RNA, which can tackle the important problems about RNA, whether RNA processing, for instance, how the splicing is going to happen, and how stable the transcript is. With that, we have some typical models under the scope. For instance, for the gene expression, we have DeepSeq, passenger informer. I briefly mentioned informer later on, and on the RNA space, there are models like MSplice, Splice AI, or Saluki that is focused on mRNA stability. I first talk about RNA splicing. We know after transcription, we end up with premature transcript, which has parts corresponding to the intron and parts corresponding to the exon. And splicing means that the cell decided to need to cut out the parts corresponding to intron and rejoin the parts corresponding to the exon into a mature transcript. And that can use for protein translation. But this can happen in various ways. And for instance, the cell might choose to include or exclude the exon in between, which leads to two different so-called isoforms. And these two isoforms were translated into two different proteins. And this is actually a way for the cell to have one gene but encode for multiple slightly different proteins to increase the diversity on the protein level. This is all good, but this can also go wrong. When it goes wrong, it sometimes has very severe consequence. For instance, in this case, this is a three exon structure, and in the healthy people, the three exons will concatenate and join together to form a mature transcript. But when, for instance, if you have mutations, some patients have mutations on one of the exons, this will lead to skipping of this exon in between, and which will be leads to an unstable protein translated. So some of these mutations actually cause a disease called spinal muscular atrophy. This is the leading cause of infant mortality, and it's estimated to affect 1 out of 6,000 or 10,000 newborns. And also estimated that approximately 1/3 of all disease-causing mutations, they cause disease by affecting splicing. That's why we're interested in to build sequence models, take sequence as input, and properly predict splicing outcomes. So how do we do that if we want to use sequence as input and predict splicing and output? We first need to And the input is very clear, but what is output? And what do we model? And what's the objective function? In this case, for alternative splicing, we have something called splicing ratio. That is a ratio between the different transcript isoforms. And this kind of ratio can be quantified through RNA sequencing, and you map the reads to corresponding to these two isoforms, and you count them. In the end, you count the fraction of these two isoforms. That is something called psi. Is computed as the fraction of these isoform among the total transcript from that gene. And the variant effect can be then quantified properly as the psi difference between the reference sequence and the alternative sequence with the mutation. So now the question is, can we build models to predict psi directly? And can we, even better, can the model used to predict variant effect, which is quantified by the psi difference? Obviously, the answer is yes, and one type of the model by far is a convolutional neural network model. Although very simple, but it's actually very powerful for this kind of applications to model DNA or RNA sequence. How it works is on the input space, you do a one-hot encoding of the DNA or RNA sequence into a 4×L matrix, where L is the length of the sequence, and 4 corresponding to ATGC, the 4 alphabet letters. And with this matrix as input, the convolution filters then scan through the sequence to detect sequencing patterns. While this filter scanning the sequence, detecting sequence patterns, this is exactly very similar to what happens actually in the cell, because what happens is that the proteins which bind to the RNA scan through the RNA and look for sequence elements, and exact the similar here that the filter look for sequencing patterns. And then when the filter matches sequencing patterns, this will activate, and after a few layers of convolution, you can even model the interactions between those elements, the same as what happens in the cell, that the protein recognizing the elements and interact with each other. In the end, you have some convolution and fully connected layers. In the end, you want to predict some quantity, and in the case of splicing, will be on the splicing level. So these are very basic model, but so far, these have been very powerful and very successful in the scope of genomics. So the example I want to show here is MNSplice. It's a splicing model that actually was the winning model for the critical assessment of genome interpretation challenge focused on splicing. This model predicts the psi, delta psi, or the splicing level change on the log scale. So what that means is that, for instance, you have these two transcripts, one with and one without the exon in between. Sometimes you have mutations, and then what you want to predict is what's the expected splicing difference with and without the mutation, quantified as delta psi. So this is a convolution model, and on the x-axis is predicted, and the y-axis is measured splicing level change with the mutation. So this model works well, and this model works well, actually works better than the previous model at that time from Cell and Science. That was the case of you have an exon in between that you decide to skip it. And there are other cases where, for instance, here is a transcript that is longer than the other. And for those cases, the model also works well. So we mentioned before that the convolution filter is scanning through the sequence to detect sequencing patterns. Here are some visualization of the sequencing patterns learned by the model. So these are sequencing so-called motifs. These are motifs seen as something like this, and these are corresponding to well-known RNA binding proteins that these are well-known elements that are recognized by RNA binding proteins related to splicing. This is just to show that the model actually learned something about biology and use that to predict relevant information about splicing. So that was good, but however, we know that splicing happens tissue-specific, which means that in different tissues, the splicing happens slightly differently. For instance, in the brain might be different in the blood. And for many applications, for instance, if you want to test something for the patients, the blood is very easy to get, but other tissues might be more difficult. So ideally, you want to measure something in the blood and can infer for other tissues which you cannot take sample from. For this, we need a tissue-specific model. And the model, again, is a very simple convolution model that has convolution filters and a few layers of convolution. And in the end, you have only the last layer is specialized for different tissues. We train this jointly as a multitask learning model. So now with a tissue-specific model, hopefully the model also captures tissue-specific variant effect. We then try to apply to some real patient data. This data collected from this study is about autism spectral disorder. Autism is a class of neurological disorder that is people with ASD tend to have problems with interaction and communication. This is classified as a rare disease, but actually it's not so rare because, for instance, in the UK, 1 out of 100 people are diagnosed or actually is a carrier of the disease. So what's nice about this particular data set is that we get data from both parents and also both siblings. And in this case, only one of the siblings is sick, which means that because the family shares broadly the genetic background mostly, and but only one of the kids is sick. Therefore, we know that the mutation is very likely, the mutation that caused the disease is very likely coming from the de novo mutations happens specifically in the sick kids. De novo mutations are mutations that are not inherited from the parents, but really happens in that generation. This is a very small subset of variants among all the variants you can identify from any individual. On average, each of us carry like 100 de novo variants, so that we can, because of this study setup, we can focus on very narrow subset of variants that are easy to handle. So now we ask a question whether when we run our model to predict the variant effect identified from these two siblings, do we see any difference between the patient group and the control sibling group? Do we predict much more severe effect for the disease group? And this is indeed the case. If we look at all variants, basically all the de novo variants we identify from these patients and siblings, we see a much severe predicted effect for the disease group compared with control group. And then the effect is much larger when you restrict to the genes that are more relevant or functional important, or so-called loss of functional intolerant genes. And next, we want to see whether there's any tissue-specific effect. And indeed, we find that in the predicted effect is much more severe in brain compared to other tissues, which makes sense because autism is a neurological neurodevelopmental disorder. Obviously, the effect in brain is much more severe. So with that was model on RNA. And next, I want to talk briefly about a model that takes DNA sequence as input and predicts gene expression directly. In this case, the model tried to predict different quantities or different measurements related to gene expression, including gene expression level and some other histone marks. These are experimental data that measure genome-wide. Therefore, the single model takes DNA sequences input and try to predict all these different tracks. We call it experimental tracks. And the model Informer was the model informer is actually a hybrid network that has convolution layers in the bottom, and then some layers of transformer blocks try to model properly the more complex interaction between the sequence elements. And then another nice thing, other than the more interesting architecture, is that the model actually has a much broader receptive field, means that it sees sequence far more beyond compared to previous models. In this case, the model takes a 200 base pair sequence as input, and it predicts a large amount of tracks. With that model, we want to answer the ultimate interesting question, which is, if we have mutation on the sequence, does that model capture anything interesting about the mutation, about the variant? In this case, it's about gene expression, right? So this was done by testing some EQTL variants. EQTL is an association study that tried to associate variants and gene expression. In this case, there were some causal variants that link to gene expression, means that they affect gene expression. And in this case, it's a binary classification where there are variants cause or do not cause gene expression change. With that, this model actually works way better than the previous Bayesian model on this task. So that was models built on top of DNA or RNA sequence that predicts things like RNA processing or gene expression. We are also interested in there's another type of sequence, which is protein sequence, right? This protein sequence has 20 alphabets, slightly more complex maybe. And the models that trained on protein sequence, they can do things they are meant to do things. For instance, that I briefly talk about like representation learning. For instance, if you train make an unsupervised model on the protein sequence, can we make use of the model for any downstream task? Does that improve the performance of my downstream task that I'm interested in? For instance, if I have very little annotated data for my downstream task, can a pre-trained model, a powerful pre-trained model, help in my case? And also, we are also interested in protein variant effect prediction, because many of the disease actually caused by changes, mutations on the protein. And obviously, there's some effort on predicting protein folding. So I think by now, we all know what language model, and we are familiar with the term language model, which was typically meant for the language we speak. But you can also train protein language model, which means that you train a language model on protein sequences. And this type of model are typically trained from a very large complex. By very large, I mean millions of, 100 millions of protein sequences from all organisms or across the evolutionary tree. And with that huge amount of sequence data as input, we try to train some language model. In this case, this is an example shown as a masked language model, which means that you randomly mask out some of the amino acids in the input and try to fill the gap. And this type of model are typically, like a regular language model, a stack of transformer blocks. And they are trained with perplexity as a metric, the same as other language models. And the performance, what's nice about this model, the performance also scales with the model size scale and the input data scale. And this can be fine-tuned for more specific tasks. In the end, after you train a protein language model, in the end, the model is capable to predict the probability of every possible amino acid on every position, which is, in the end, you can predict such a map, right? Each dot here is a predicted probability of amino acid at a given position. So for the downstream task, after you train this protein language model, for the downstream task, this is one example I want to show, is about antigen presentation. So a very quick introduction to antigen presentation in immunity. is, for instance, what happens here? For instance, you have a viral infected cell. Now, what happens in the cell is that the protein or the virus digests down into protein fragments. And the cell, what it does is they sample randomly among these peptides and present them on the cell surface so that the cell has a mechanism, has a chance to check whether this piece of antigen is from self or from, say, a viral infection. And hopefully, the cell can detect there's a viral infection, and then the T cell can come to kill the infected cell. In this process, the antigen presentation process, MHC and antigen interaction or binding is a vital process in this case. So for a computational model, then the task is, can we predict, given the MHC and the antigen, can we predict whether they bind, or can we predict whether the antigen will be presented by the MHC or not? So you can imagine this is a task taking protein sequence as input and try to predict something like binding or antigen presentation. BirdMHC is a model for that. This is a model that leverages on pre-trained large language model on protein and then fine-tune it for this specific task. It takes MHC and peptide, concatenate them as input through a pre-trained model. And the pre-trained model will be adding an adapter, which is a small network, MLP network, try to predict binding or presentation. And then the whole network will be fine-tuned for this small label data. What we want to show here is that the unsupervised pre-training part is vital in this process because it not only leads to a better performance, but also the model converges much faster. So here on the x-axis, on the left panel, the x-axis is the training epoch, and the y-axis is the performance. And this curve is the curve corresponding to the model used pre-training. And we see that the model converges very fast, and even with a very small amount of training, even one epoch, the model already outperformed the other model that trained from scratch. And what's also interesting is that the model is also very robust to the amount of data you use. The model not only the model used unsupervised pre-training can even train on like 10% of the data without sacrificing too much of the performance, which means that this kind of approach is very applicable if you have a small amount of label training data. And overall, the performance is really good, and it outperforms the previous state-of-the-art on the predicting the binding or the binary presentation task. So we are also interested in predicting protein variant effects. Right? The protein variants are, you have a mutation on the protein, and you are interested in whether that causes disease or not. And in fact, often cases it does cause disease. And this is currently a remaining challenge to be solved. And in fact, this some paper by Brandes et al. So in fact, after you train a complex or a powerful protein language model, you get a variant classified by free. Because remember what the protein language model does is to predict the likelihood of all the amino acids at any given position from the protein sequence, which means that you have a likelihood map of all the amino acids on all the positions. And if you are interested in, for instance, in this case, what's the predicted effect of mutating an arginine to a histone? This can be modeled by the protein language model as the predicted log likelihood ratio of the reference amino acid H over the alternative amino acid R, which means that if this likelihood ratio is high, which means that the model thinks is very likely that this kind of substitution to happen, which means that this is probably benign. And if the model thinks that this kind of substitution is very unlikely to happen, which probably means that it's very bad because after training the model thinks this is very unlikely. So with that, you can predict actually proteome-wide at every possible position
the predicted variant effect. And in fact, this works very well. That, for instance, in this plot, x-axis is the log likelihood ratio, score for all the variants. And here, the color are color-coded by some existing well-known database that annotate whether a mutation is benign or pathogenic. And you can see that the scores actually separating this very well. And in fact, this kind of approach, even though never trained for this task, it is completely unsupervised trained, like a language model, but it's already outperforming some model that dedicated is trained for this kind of specific task. This actually shows that this kind of representation learning or unsupervised self-supervised learning is actually super powerful to understand the distribution of sequences. With that, we broadly spoke about DNA, RNA sequence and how we model protein sequence. Hopefully, we get a sense that deep learning is a tool to read these kind of biological sequences, and this is when the model scale and the data author scale, we try to leverage on the continued growth of experimental data, which is getting better quality, higher quantity, and more modalities. And a large part of genomics is really trying to understand genetic mutations, and this kind of sequence-based model is really a powerful approach to understand that. And in the end of the talk, hopefully, we get more people interested in this topic and work on these important challenges. With that, I want to thank for the people that I closely work with, and also thank for your attention. Looking for questions.
Thank you so much for the informative talk. So as people start coming up along the mics for questions, I was just struck by the broad sort of applications that you presented for machine learning. It's exciting to see the broad range of tasks that you were presented. And maybe we can start with the question here, and I have one.
Sure. Hi, thank you so much for the great talk. You made a great case that large language models and pre-trained models have been so useful in the world of modeling proteins. I'm wondering, where are those models for DNA sequences and for like the gene expression prediction tasks? Is it that there are not the same sort of universal rules that there are for proteins that there are when you compare between organisms, and what's your thinking on that?
There are definitely some efforts to try to do language model on DNA sequence. However, there are some challenges there, just because, by definition, DNA are 3 times longer than the protein because triplets encode for 1 amino acid. Mm-hmm. And these kind of, like the transformers, they scale quadratically with the length of the input sequence. So the technical challenge is higher there, first of all. And second, the biological information on the DNA sequence, because imagine like only 1 to 2% of the genome is encoding for proteins, and 98% of them, God knows what they do. And it's very challenging to model them already. And the unsupervised model, the information that you can gather is very sparse. That you probably need clever ways to properly sample the input sequence for that. And there's some effort starting doing that, but not very successful yet.
Great, thank you.
Hi, great talk. So for language, for like protein, for unsupervised training of protein language models, do you think like masking is the best way to go? Because like masking in protein language is very different than masking words in a sentence. So I want your opinion on that.
Are you asking whether masking is the right approach? Yeah. Well, empirically, what people see is that there are 2 ways you can do that: a generative way or a masking way, which is either a decoder only or encoder only model. So the masking approach is actually very good. Empirically, they are very good for representation learning. A model trained as a mask language model, they're good for downstream fine tuning. And the other generative approach, empirical study shows that they probably worsen on the representation learning part, but definitely there are some other applications with generative trained model. For instance, if you want to do some designing on the sequence, then probably you should go for the generative approach. They are meant for different purpose, I think.
Thank you.
Hi. Thank you so much for the nice talk. And so, I'm not, genomic person, and so I'm natural language processing. So language model works for the natural language processing because we have high dimensional space in the words. But my understanding for the genomics, and you have ACT, and it's with limited space. So by saying so, and we also, my basic knowledge in biology is that even though we're different from the mice and human and mice and rat, but our genome share like 90% similarity. So can you leverage in terms of what we care about human is not about we share lots of things in common. It's something we don't have in common. We have mutation caused diseases, and lots of those mutations, they're real mutations. How would you envision that this language model actually help us to identify these real diseases and not actually overshadow efforts to identify those minorities?
Yeah, that's a great question. So, well, there's definitely a lot to work on, but I think what the language model does when they train unsupervised on those sequence from different species is that they are trying to learn the evolution conservation. Right? They do some sort of alignment. They say, well, I see this sequence before, I see this very similar sequence also from mouse, and some regions are more conserved across species and some are not very conserved. In a way, it's a more fancy version of conservation, saying that some are more conserved, some are less conserved. Yeah, I think, for instance, in rare disease, traditionally people do some conservation-based scoring, and I think this goes to this similar spirit as that. Does that answer the question?
Hello, thank you for your great presentation. And I know there are many works predict the pathogenicity and the benign of the missense variants using the protein sequence with the protein language model. But it only indicates the pathogenicity and the benign property. So, but there are many missense variants that I just wondering how to link the variants to the phenotypes because they don't just give the binary, not the disease-specific properties.
Yeah, so predicting like benign or pathogenic or kind of fitness is, I would say, is simpler than predict which of the phenotype, because phenotype, there's a very large space of phenotype and very little annotation data. It's just, I personally found it super challenging to predict phenotype. I think the first step is to, understand predicting the fitness, and then we try to relate the fitness to phenotype through some other method like GWAS, like an association study, like try to link variants to phenotype.
Okay.
Directly predicting them, probably challenge.
Okay, thank you. Okay, thank you.
Thank you.
So in the interest of time, we'll take just one more question.
Thank you. Thanks for the talk. So in the large language model that we see every day, the GPT of the world, right? Like we've seen a huge trajectory of improvement between the version 2, 3, and version 4, etc. Depending also on the fine tuning and reinforcement learning that you do on top of the pre-training. Where are we with protein language models? Are we at the 2 level, at the 3 level, at the 4 level, and what is needed to take them to the next step?
So at the moment, this kind of protein language model is basically borrow the exact same setup in, let's say, natural language to protein. So I see this as a very early stage that trying, to do that, because protein might be different. than natural language. We might need something specific for proteins, but so far we just borrow things over and, so first of all, it's not very clear how we can scale this model, how much this model can scale. And second, it's also not very clear how we evaluate the model. Whether perplexity is a good metric or whether we look at some other effect is also not clear. I think it's very early stage at the moment. Yeah.
Okay. With that, thank you so much for the talk.
Thank you.
So next we have a set of oral talks.
So I'm going to jump us right into the next session. I'm excited to introduce what will be the next 4 oral talks that we'll have before our break and first poster session out in the lobby today. So that'll be quite exciting. So with that, similar to the first session, there'll be 12-minute talks with some time for Q&A. So think of those exciting questions that we've been having all day. And with that, I'd like to introduce the first talk, which is going to be on collecting data when missingness is unknown. And the speaker is Kevin Wu from Stanford University and Optum Labs.
Hello? Okay, this is great. And okay, hi everyone. So my name is Kevin. I'm a PhD student at Stanford. And today I'll be talking about work that I did while working with Optum, this United Healthcare, and a data science team they have there. And in general, they're interested in the healthcare algorithms that they're deploying on patient populations, and these have a lot of different potential applications. But in particular, it's about deployment issues and things that happen when the algorithms are used on different populations and so forth. So today, the presentation is specifically about collecting data when missingness is unknown. So I'll cover a little more about what that is and what we find from there. So yeah, as a motivation, EHR-based ML algorithms are being deployed on patient populations, and interestingly, they're not sort of FDA regulated at this moment, and they are used on patient populations in a variety of different contexts, and they're very diverse in terms of the use cases that they are used on. But in general, they use some combination of historical patient data, and they might even use some real-time patient data coming through the EHR, right? So this sets up where we have the system where there's a data pipeline of EHR coming through, and then there's some algorithm, and then at the end there's some result. And so naturally, when the EHR itself becomes unreliable, then what we get out of the EHR data, what we extract from patient records, becomes unreliable as well. So here's like a schematic about what I'm talking about here. So on the left, we have one patient attributes, and let's say this model takes in just a few binary input variables, and the outcome is some disease, and we have some score associated with that, right? So specifically in this talk, we'll be talking about data corruption that happens on binary attributes. And so let's say there's 2 features here, which they were supposed to be 1s, and they just turn out to be 0s because of some data corruption process. And that changes the predicted score that we get from this. So we don't want this to happen. We want the performance to essentially stay as accurate to the patient's true risk score as possible. And so this specific phenomenon I'm talking about here is something I'll talk about, which is which in the paper is called latent missingness. There's different terms for it in literature, but in particular, latent missingness is when there is missingness in the data that is unobservable. There's some mathematical formulation here, but I'd rather describe it in terms of the code. So this is something that I've written before, where you have a feature, for example, that you want to know whether a patient has diabetes. And so you look into the patient record, and you might look at something like their A1C score. Right? And so you might create a binary variable here. This is if the A1C is greater than 6.5, call it a 1, and if it's not, then we say it's 0. Another example might be whether a patient has asthma. So there's a specific ICD code associated with that, and if it appears in the patient records, then it's a 1, and if it doesn't appear, then it's a 0. So the issue here is that when it doesn't appear, that whole subcase also covers when a patient just doesn't have that record. And that happens a lot. There's missingness happens. But we just don't have a record for that a lot of times. There's not some indication that says this patient doesn't have something. It just doesn't appear. And it may not have a checkup for it, or they might have done it at a different hospital. We just don't have the data for that. So in that case, we end up with this situation where we just don't know how to address the data problems here. One class of ways to solve this would be model-oriented, model-centric, and there's also literature in terms of how to be robust to different variations in the data, how to create good classifiers that account for this. In particular, we're going to assume the situation where the model is locked. There's a couple reasons for this. It might be that the algorithm's already shipped and you don't want to keep swapping in the models. It might be that it's hard to retrain models on the fly. So we're going to focus on the data-centric model, where we actually collect potentially missing data. Right? So in the context of United Healthcare and Optum, they might have some kind of a budget dedicated to fairness of algorithms, and they can just allocate this budget to actually collecting and cleaning data points for future use. So for example, it could be something like a subsidy for patient checkup. So if these are like things that you can cover in a patient checkup, you just say we will subsidize partially or wholly a yearly checkup, annual checkup, something like that. They could also be specific biomarker tests. Those cost money. You can also say we'll do some for free for a subset of population. It could also be patient self-reporting, some questionnaire. And then finally, we have some things like manual data review. Physicians can do chart review on patient records. So all that sounds good, but what are the technical challenges to this? So the first part is that not all data costs the same. So it might be some specific biomarker might cost a lot of money versus a checkup might be pretty cheap. The second thing is that they are not all equally valuable to the model. So if we just took all the missing data and we started to collect them at random, it may be that some are very informative features and some are not very informative. So we have these kind of competing sources of information. And finally, we have a limited budget for data cleaning, data collection. And so if data collection is costly, in an ideal world, we'd like to collect all the data for all the patients all the time, but we just have a limited budget here. So how do we allocate that budget? So we're just going to do like a first principles look at this. So in general, we have this optimization framework here. So we're trying to maximize the value of data collection. So this year we just put it here, let's call it V. And then we have it subject to some cost that every data point for every patient has. And then finally, we have these observation indicator variables to say, either we observe it or we don't observe it. Either we pay the cost or we don't pay the cost. And finally, there's some budget that we want to keep under, ideally. So we'll focus specifically on what value means in this case. And so we're going to define value as just the reduction in model loss if we were to collect this one data point. And here we're assuming this like linearity between data points, but basically we say that every data point we collect can reduce model loss by a little bit, and we want to just maximize the total model loss that's reduced. Okay, so if we were to just do like a Taylor approximation to what we just saw there, the difference, we get three different things that it turns out to be. So first is the change in X, which we don't know, right? We don't know if we're actually going to yield a positive value for any data collection. So there's some kind of unknown kind of randomness to it. And then there's feature sensitivity, which is how much the collection of that feature changes the model's output. And finally, we have this loss sensitivity, which is basically akin to saying how much, at this certain point, how far are we off, how much are we deviating from the true patient prediction. And so the thing is, we'd like to have all this, but reality is we only get access to the middle one here. Like, we don't know what's going to happen in data collection. That's why we're doing it. And also, we don't know the true label because this is happening in real time on a patient population. So what we're going to focus on is how do we best estimate feature sensitivity in the context of what we do know. So there's just a few things we can do. So the most naive thing we can do is just compute feature sensitivity. We just look at the difference in model prediction, which we can do. That just takes a forward pass through the algorithm. But there's feature interactions that we have to worry about in any algorithm. And generally speaking, when we look at things like feature interactions, there's a bunch of different ways to handle it. But Shapley value is one that's pretty common, and that takes into account higher order interactions between features. Right? So all that looks fine. But the specific technical contribution that we're making here is that not all the coalitions matter if we were to just apply a standard Shapley value here. And so just to illustrate what that means, we have, let's say, 4 features, and we're trying to estimate what happens if we were to change the green feature here. Right? And then the dotted boxes are the ones that we don't know, but we do know we've already collected what we're sure about, the second value there, the 1. So if you were to look at the 2 to 4 different coalitions that we can look at for a Shapley value. This is how we would compute it normally. We just look at all the different feature changes and we just compute that sum above. But if we're actually looking at what might actually happen in real life, since we already know the second feature, then not all these coalitions matter. They don't actually appear in the data because we're not going to collect that feature. Right? So it's a very straightforward way to look at how Shapley values are computed. So how do we take into account feature sensitivity for this observation that we are going to make on the features? And so we're just proposing here there's something called the observation-dependent Shapley value, which is we're only looking at the subset of features which are going to be changeable or potentially observed in the data set. And so we're just taking out parts of the coalitions that are computed in the Shapley value. And so there's a tweak here in this formulation right here. Okay, and then after that, there's a specific algorithm, and here's a schematic for it. So we have an initial test set. So this could be a patient population that algorithm is being deployed on for a certain hospital, a certain period of time. And then we look at this potentially missing data. Here's all the data that we don't actually have collected, and it could be a subset. It could be only the binary attributes we care about. The second step is we estimate the value of collecting each data point using the observation-dependent Shapley value. And then after that, we apply a straightforward 0-1 knapsack algorithm under a constraint budget. We just run that algorithm. And then finally, we get a subset of the data that we want to collect that keeps us under budget. Okay, so the next step is just the experiments that I'm going to run through a set of experiments just to show what we get if we were to take into account observations. So we look at a Mimic-4 data set, and there's 3 different outcome variables that we ran models for, and then additionally we have a simulation data set as well. Okay, so the way to interpret these graphs is on the x-axis, we have a fraction of the total budget, and this is the total budget here is just the amount of money it takes to collect all the variables, and so 1 would mean that we just collect everything. And then on the y-axis, we just have the model improvement in terms of the delta and the AUC. So basically, we want to be upper left. That's where the happy spot is. So the red basically is the method that we're proposing. And then we have the gray is random data collection. And we have 2 other baselines. One is just feature gradient, and that's if you're just looking at the model, the change in model prediction we talked about before. And finally, green is the standard Shapley value without any account for observation dependence. And so we see here that across these different experiments that we do get the most improvement and most efficient data collection if we were to take into account observations when we're computing the value of data collection. And another way to look at this, if we were to squash these curves, is on the top right. Basically, this is just the net improvement that we get. Right? So it's a very natural kind of result we see here. This makes sense in the context of data collection. And then finally, we have another set of experiments here, which is what if we were to vary the cost structures? And so the previous experiments just had uniform, the same cost for every data point. And so what if these we have some randomness so across a uniform distribution? If there's some randomness in cost, and also the second part here, what if they're exponentially distributed? There's some experiments are way more expensive than others, and we see that we also still see that improvement here. Actually, see some more improvement because the knapsack algorithm is able to work more of its magic. And so it's robust across different variable cost structures. Okay, yeah, that's basically it. The takeaways are basically we want to just, the point of this research was showing that data collection is one way to handle missingness, types of data corruption, and just to encourage health providers to think about actually using the money towards specifically improving the quality of the data, and that could be a direct way that you can titrate out budget / algorithmic improvement in the context of using these ML algorithms in clinic. And yeah, and these are my collaborators.
So we have time for a few questions. If not, I've got one I can actually ask right off the bat. So it's a fascinating talk. I guess part of this is sort of forward-looking in terms of where you can go with this. It's fascinating with respect to the amount of data you can collect. I wonder, you had an assumption in the beginning. You said you're not differentiating missing at random and missing not at random. And I think we know in a lot of these clinical settings, sometimes some of the data is missing not at random. So it's not observed because the doctor did not prescribe some lab or evaluate something. So do you have any insight on how those two differentiate what would be sort of the results you find here?
Yeah, that's a good question. The reason why we're not making assumptions about randomness is because in this experiment particularly, we just don't have real data on missingness, right? We have to make some kind of assumption about it, and so we just generate it. So we'd like to include it here, but in some ways it felt like I was just creating an imaginary world and then saying I conquered that imaginary world. I think the next steps for this research is to gather real data in terms of missingness. We can sort of tack on modeling of the types of missingness and add that in to part of the equations as well if we do have that data, so yeah.
Very nice talk. I have a quick question. Maybe you're expecting it about scaling. So Shapley values scale very poorly, at least the true one. In your case, if you're cutting down the number of coalitions, you will still scale exponentially on the number of features you want to impute, right? So do you guys have a solution for that, or you still try to calculate the exact values? And then the other side is, so you've shown us something that works for binary features. How do you reflect on the scaling on non-binary features?
Yeah, great questions. So for the first part, we don't, we're still bound to the laws of, Shapley value calculations. The observation dependence does cut back the amount of coalitions we consider. And in practice, we're using different kind of ways to make Shapley value calculation quicker, like tree shap and so forth in here. But at the end of the day, we're still calculating across all these coalitions. So it does get limited depending on the types of data set we use. And then with the extension beyond binary variables, for here, we're just interested in this missingness that's unknown because for continuous variables, the value of 0 is kind of it's a rare thing that it could actually occur as a value. Like you won't have an A1C of 0 necessarily, and people might know that's just actually missing data. So that's why the binary component makes it ambiguous, but there could be other categorical situations where that also is ambiguous. So we can extend it to other situations, it's just that it lends itself to the binary case more so.
Okay, we have time for maybe one really quick one.
Might be more a clarification. By the way, it's good talk. You mentioned, so is there an assumption that your model, as you mentioned, is locked? So does that mean it's also trained on a complete data set, do not have the missing data? And in a real case, our training data might also have some missingness. So how do you plan, maybe you cover in this paper, but how do you plan to address this kind of missingness in the training data?
Yeah, very interesting. So we're assuming that there's not missingness in the training set, but there always is. I think the assumption here is that there's going to be a relatively higher quality of data used in the training data. So when they're collecting attributes, there's some kind of a validation to it. And in general, like if we were to look at kind of theoretically what happens, we only can get as good as, so the more error the model inherently has, the worse this performs, because as we're collecting data, we only get as good as the model itself can be tuned to the data set. So there's a bit of trade-off there.
Let's thank our speaker again. And we'll move on to the next talk here on large-scale study of temporal shift in health insurance claims data. This is Christina G. from MIT.
Thanks. So what a lot of historical models would do, previous work would do is they would look at like a model from like 2019 and to see how does the performance change in 2020. And what we propose instead is like fitting a new model in 2020 and then comparing that performance in 2020 to the performance of the 2019 model. Because intuitively what we're trying to say here is we want to be able to use the new data to update the model, and there's only room for improvement if that a model that was fit on sufficient data from the new time point is actually able to do better. So what are some motivations for doing the retrospective study of temporal shift? Well, first, if we can look back in time, that helps us identify potential causes of temporal shift, because at this point we have the data to fit the new model. And then if we monitor these causes in the future, then that can help us detect temporal shift earlier in the future, even if we don't have the data to fit a new model. Another motivation is that once we have these historical examples, we can then try out different strategies for improving model performance when there's limited data, and then in the future, those same strategies can be deployed. So here we're going to formalize what we mean by temporal shift. We say that an outcome at time t is affected by temporal shift within the subpopulation ht if this equation holds. And here phi is so phi here is the metrics for that we try to use it to evaluate clinical impact, and you can define it any way you want. So here we use AUC. We evaluate this metric on the data set at time t, And the models that we're comparing are the model that are fit on data from time t and the model that's fit on data from time t minus 1. And both of these models are being evaluated on the subpopulation. So putting this together, what our definition says is that temporal shift occurs if the performance of a model fit on the current data and then evaluated on the current data is better than the performance of a previous model. And this is in contrast to some prior works that compare the performance of a previous model on the previous data to the latter. And I do want to note here that a lot of works, prior works also use the same definition we do. I just want to define it so that we can then use it in our algorithm to test for temporal shift. So there's 3 steps to our algorithm. First is to learn models to predict the outcome from features prior to the prediction date. And we fit 2 separate models for the times t minus 1 and t. Then we discover a subpopulation that might be affected by shift. And so this subpopulation that's being evaluated could be like the entire population of patients. It could be a predefined subpopulation based on disease etiology, or a way to automatically look for subpopulations is to label the samples based on where the current model is better calibrated, and then fit a new classifier to predict those new labels from the original features and outcomes. And this gives us a more generalizable description of the subpopulation that's being evaluated. So with the outcome model and the subpopulation, we can then test the definition for temporal shift. So first, we look at the validation data to see if the models are well fit enough to describe the distribution and if the confidence intervals for model performance suggest that the definition might be satisfied. Then we move on to using the test data, if these criteria hold, to perform a hypothesis test for our definition of temporal shift. So putting that together, the 3 steps are to learn outcome models, find the subpopulation that might be affected by shift, and then test our definition. And here to point out that if we're doing the baseline version, we would plug in the baseline definition for the test in the last step. So now we have a way to test for temporal shift. We want to use it in a large-scale study, so we then propose an algorithm to scan for temporal shift. And the goal here is to be able to scan for shift across many different outcomes in multiple time periods, and either within like the entire population of patients or within discovered subpopulations. So the algorithm to scan for shift, first we apply the test for each individual task separately. Then to account for testing multiple hypotheses, we then control for false discovery rate, where we only account for the task that has satisfied the criteria on the validation data. And then at the end, we examine clinical significance to see are the cases that are identified, are they clinically meaningful. So we demonstrate our algorithm on a large-scale scan for temporal shift in health insurance claims. Here we are assessing annual temporal shift from 2015 to 2020 on over 1,000 tasks. These outcomes are defined by whether an insurance claim code occurs in the patient's data in the next 3 months. And we select the most frequent initial condition diagnoses, abnormal lab measurements, and procedure groups. We have a larger data set with over 1.6 million patients and over 15,000 features. So here's an example of a task that is affected by temporal shift. We're looking at the colonoscopy procedure, where here we are plotting the performance of the model fit on current data and the model fit on previous data as evaluated on the data in each year. What we see is that in 2020, the current model is significantly better. And this aligns with clinical intuition because colonoscopy is one of those non-urgent procedures that was postponed during the pandemic, so that leads to label shift. And then also there are many other features that were affected during the pandemic, and that leads to domain shift. So how do our algorithm and the baseline then perform on this task? Well, here we've plotted the confidence interval that our algorithm computes in purple, and the one from the baseline in green, and we are comparing the intervals to the statistical significance threshold that's in the dotted black line, and we're also comparing the point estimates to a clinical significance threshold in yellow. So first, if we look at 2020 here, what our algorithm is comparing is the difference between the model performance for the 2019 and the 2020 model in 2020, and that is above the thresholds. In contrast, the baseline is comparing the 2019 model performance in 2019 to the 2019 model in 2020, and that would fail to capture that the model could potentially be improved. So in this task, only our algorithm is able to detect that there is shift in 2020. And then on the other side, here's a task that does not have temporal shift because the models perform similarly in each year. And we see from the purple intervals that our algorithm does not detect shift in any year. But the baseline erroneously sees shift in 2018 and 2020 simply because the outcome in those years are harder to predict and performance drops. So now that we understand sort of how the algorithms work, we can look at some of the results from the large-scale study. So here we've plotted the proportion of tasks for each outcome type in each year that are affected by shift as detected by our algorithm in the solid lines and then by the baseline in dashed lines. So first we see that around 10% of tasks are affected by temporal shift. Majority of those fall in 2020 during the pandemic. And prior to that, lab outcomes tend to account for more examples of temporal shift because lab concept codes and availability tend to change more over time. We also saw that in 93% of the tasks, the subpopulations that were identified by the algorithm were affected by temporal shift, and that suggests that if we were just to monitor for shift at a population level, that would be insufficient to determine when we need to train a new model because we would be missing when some groups of patients would be adversely affected. And then finally, to understand some of the clinical motivations, we first looked at some case studies. So, for example, we saw a lot of the tasks occurred were in 2020, so we looked at for domain shift by looking at univariate covariate shift, and we found that there were over 700 features that were affected in 2020. Then another example was the low EGFR lab outcome, where 4 out of the 6 outcomes showed temporal shift in 2018, and this was driven by a switch from the MDRD to the CKD EPI formula that year. And one way to address that shift is we can then combine those 6 outcomes into a single outcome, and then if we fit a model to predict this combined outcome in 2017, that would work well in 2018. And then the final example here is inpatient consultations. So we saw a swift drop among patients who had coronary heart failure or atherosclerosis in 2019. That is also reflected by a change in how the feature was used in the model. So when we talked with the insurance company, we found out that the Medicare reimbursement policy that year stopped covering inpatient consultations, so doctors stopped putting in that as the billing code for Medicare patients. And then these two conditions are much more frequent among Medicare patients, so they served as sort of a proxy for Medicare status in the model, and that explains why we saw this conditional shift. So the takeaways from the case studies are that we can then look for similar concept policy or clinical practice changes in the future to help us detect temporal shift earlier. Also, we can do adaptations of feature or outcome definitions based on the clinical knowledge. Then that will help us create these models that might be more robust to temporal shift. So to summarize our contributions, first, we formally define temporal shift by comparing the performance of the current model and the previous model on the current data. Then we create algorithms to test and scan for temporal shift. And with our algorithms, we find that temporal shift is very prevalent in healthcare data. So I'd like to thank many people at the Independence Blue Cross at MIT for their input on this work, and I'm happy to take questions.
So we have time for some questions. Yep, go ahead.
Thanks for the talk. I have a question on the definition of shift. So the way that you define the temporal shift, it seems that it is dependent on the model. So I was just wondering, like, the thought process behind that, because if I have like a poor model which is kind of invariant to the data set that I evaluate it on, then I will not detect a shift.
Yeah, so one thing that's important is to pick a model that is sort of well fit enough to the data. That's why it's one of the criteria in like the validation step is to check for that on the validation data before evaluating the definition. And so like it's generally like sort of a choice for a user who doesn't use the algorithm to pick a model that works for them.
Hey, thanks for the talk. So I was wondering, it seems kind of compute hungry in that you have many time steps, many different tasks. Also, I saw some bootstrapping for the confidence intervals, which you also need, right, for like statistical testing. So is this scalable? And second question is like, if 93% of the task change, should you even test or should you just always update models?
That's a good question. Yeah, I think like if we're using this specifically for models that are in practice, then like for the individual model itself, hopefully it will not be too too expensive. Like that's like an evaluation process that probably should be ongoing anyways. And I think yeah, like updating the model I think is a great area for future research in this direction.
Okay, that's perfect timing. Let's thank our speaker again. We'll go on to the next one. So our next talk is going to be Bayesian active questionnaire design for cause of death assignment using verbal autopsies. And our speaker is Toshiya Yoshida from University of California, Santa Cruz.
Hello, everyone. Yeah, thank you for the introduction. I'm Toshiya, a PhD student at the University of California, Santa Cruz. My talk is about the Bayesian active questionnaire design for verbal autopsy. This is a joint work with Trinity, Professor McCormick, Professor Wu, and Professor Lee. First of all, I'll explain verbal autopsy. The cause of death distribution provides critical information for public healthcare planning. However, according to WHO, about 2/3 of the deaths worldwide are not registered a cause of death because many of the deaths happen outside of the hospitals. A verbal autopsy is an interview carried out with the family members of the deceased people to collect information on the causes of death. A standard approach for verbal autopsy is to ask the experts to interpret the survey result. However, this approach is time-consuming and expensive. Therefore, researchers have proposed algorithms and statistical tools to automate the analysis. Okay, before diving into details, I want to show you what kind of data set we are handling. This table displays some of the actual questions used in verbal autopsy. For example, the first one is, did the decedent have asthma? Most of the time, each question corresponds to one symptom, and the answer is yes or no, so it can be converted to 0, 1. After asking questions, we collect their responses. Yeah, like this. And the data set also includes some demographic features, but almost all of them are yes or no responses to the symptom-related questions. The objective of the verbal autopsy is to estimate the cause of death by using these responses. The current verbal autopsy practices have various problems. As you can imagine, a long VA questionnaire is a burden, although it is known that a few questions can be as informative as all of the questions. In addition to that, people also don't like the disorganized flow of questions. Oops. So we aim to reduce or shorten the survey while achieving higher accuracy and maintaining the natural flow of the questions. In order to shorten the survey, we will select the informative questions iteratively and stop the survey after having enough information to estimate the cause of death. And to avoid the disorganized flow of questions, we introduce the penalization term in the calculation of the information score. We also extend the existing framework in a Bayesian framework to embrace the uncertainty for the cause of death assignment, score calculation, and the stopping rules. Here, we use these notations. C is the ID of causes of death, J is the ID of questions, X is a matrix of responses, and y is a vector of cause of death allocation. In this presentation, we use this generic analysis model for the responses and the true cause of death. For the unknown parameter phi and the true cause of death, we can estimate in a Bayesian manner. Okay, I want to perform how the questionnaire works in verbal autopsy. First, I want to perform the normal fixed order questionnaire. Let's say the first question is about asthma. The interviewer asks the participant this question and collect the response. Okay. Then the interviewer brings the next one, collect another response, and this continues all the way to the end. As you can imagine, if there are more than 100 questions, this approach is burdensome for the both interviewer and the participant. Nextly, I'm going to perform our active questionnaire design approach. In each step, we calculate the score and pick up the most informative question based on the score. The interviewer asks that question and collect the response. And based on the collected response, we estimate the cause of death at this point. And at the end of each step, we check if the collected responses satisfy the stopping rule. If not, continue the survey. Again, calculate the score, pick up the most informative question, collect the response, and update the estimate of the cause of death. We continue this until the stopping rule is triggered. Okay, and we repeat this for each participant so that we can tailor the questionnaire for each participant. Then I'm going to explain the details in each step. First, I'm going to explain how to calculate the score. We get the ideas from the literature on adaptive design, where the goal is to select the optimal question sequentially. One of the most widely used ideas is to use the Kullback-Leibler divergence to measure the posterior uncertainty. In other words, by choosing the question that maximizes this score, we can minimize the posterior uncertainty. And in practice, we don't know the true model parameter phi, which is required for the score calculation and the cause of death assignment. In this paper, we use the following two approaches. The first one is to use the posterior mean to calculate the score, which we call the point estimate approach. The next one is the posterior predictive approach, which calculates the posterior predictive mean of the score. And we can also deal with the jumping by introducing penalization term. Nextly, I'll explain stopping rules. We make use of Sue's method. First, we specify the two values, p first and p second, and compare these values with the largest and the second largest values of the posterior probability given the collected responses. Let's take a look at this example. These bar plots show the posterior probability of correct classification given collected responses at each step. As you can see, the distribution is usually flat if we have limited data set or limited information. However, as we actively collect the responses, the probability masses are concentrated on one or two causes. In this case, we stop the survey at step 5 because the largest value exceeds the first threshold and the others are below the second threshold. We conducted experiments with a simulated data set. The first one is to investigate active question selection without stopping. We considered several different experiment setups, but all of them brought similar results. For example, look at the top left panel. The black line corresponds to fixed order. It is clear that the active ordering methods achieve higher probability than the fixed order questionnaire. The next one is to investigate the stopping rules. These tables display the questionnaire length and accuracy for different stopping rules. We can observe that the more restrictive stopping rules result in longer questionnaire with higher accuracy. We also conduct experiments with the real data. We use the PHMRC dataset. And this figure shows the classification recovery rate as the number of questions increases. As you can see, both active questionnaire design approaches achieve considerably higher probabilities than compared to the fixed order questionnaire. And it is also clear that only 30 to 40 questions can achieve a recovery rate similar to that obtained from all of the questions. And this one investigates the relationship between the accuracy and the median number of questions asked for different causes. I display 4 out of 34 causes. For most causes, that the accuracy is not sensitive to the choice of the stopping rules. And we can see that restrictive stopping rules result in longer questionnaires. For some causes like homicide, all methods achieve high accuracy with a few number of questions. This is likely because of the strong association between these causes and a small number of critical questions. In conclusion, we introduced the active questionnaire design strategy for verbal autopsy. Our approach takes into account the uncertainty from the probabilistic models. And the experiments demonstrated that the algorithms we introduced work better than the fixed order questionnaire. We need to explore the adaptive design with a more complicated analysis model in the future. Yeah. Thank you for listening.
So again, we have some time for some questions. If not, I've got one. It's a great talk. I think you see a significant reduction in the number of questions, and I guess I don't know the data set that well, but I suspect that the questions are quite broad to narrow a scope. And I wonder, does your algorithm, did you see anything in which the inclusion of one question would help it immediately eliminate perhaps dependent questions that often exist in questionnaires? Would that help us streamline all kinds of questionnaires? Or?
Yeah, I think that's, I think that, the institution that we have, so that, that's how algorithm works to reduce the number of questions. So, yeah, in other words, by using these algorithms, we can, eliminate that kind of, duplicate or really associated questions.
Great.
Hi, thanks for the great talk. I have a question on basically interpretability of the algorithm for the questionnaire and the person being asked the question. So, as in some sense, this is kind of reducing the autonomy of the agency of the question asker to kind of decide what next is being asked. So, is there a way that you can give some more inputs to the question asker about why they are being asked to go to this question adaptively?
I couldn't catch the question. So
when you decide the questions adaptively based on the responses from the previous questions, can you give some more inputs to the question asker, just in the spirit of interpretability, to give them more agency on the questions being asked?
Yeah, that's great. I'm understanding your question. So the algorithm is based on the collected responses at each step. So what was the question? I couldn't catch. Sorry.
We can follow up.
Oh yes, thanks.
Okay. Time one more quick one. Yeah.
So I also had a similar question. Great talk, by the way. I had a similar question about the early stopping, I think. So if you have like a comorbidity and you like immediately eliminate some of the questions based off of like an initial diagnosis of cancer, how can you be sure like you won't capture you will capture the comorbidity of like infection or something, maybe from surgery?
I see commonality or probability.
Or like a comorbidity, like if you have two diseases at the same time or two like co-causes of death, I guess.
Okay. So your question is like, if we assume like, the causes like multiple causes or something like that.
Yeah, yeah.
Oh yeah, we don't, yeah, in our cases, like, we don't assume that kind of things. Like, we try to assume there is one cause that brought the person into death.
No, yeah, that helps.
But yeah, that's a realistic assumption. Yeah, I'm interested. Yeah, thanks for that point.
That helps. Thank you.
Okay, let's thank our speaker again. And our next talk is titled, Do We Still Need Clinical Language Models? And it'll be by Eric Lehman from MIT.
Testing? Okay, we're good. So yes, I'm Eric Lehman. I'm a PhD student at MIT, and I'm here to present our work, Do We Still Need Clinical Language Models? And to start off, right, NLP has really shifted in the last 5 years towards the idea of a large language model, in which the definition of large is constantly changing. And this is generally done in one of two ways, in which you pre-train the model on a huge amount of text using either mass language modeling or causal language modeling, which is next word prediction. And in doing this, you build a really strong representation, contextual representation of language. And I really like this table from the T5 paper, in which they show that the architecture is important in kind of creating your language model, but the most important thing really, and what's really driving the performance of these language models, is their pre-training. So they show that on the squad data set, using no pre-training and just fine-tuning, they get 50% F1. And when they kind of introduce this pre-training step, of course, they get a 30-point boost in performance. So NLP has really shifted towards training on more and more data, as much data as possible, using as big of a language model as possible. And one thing that people have started to realize is that, wait, we should maybe hold on and really go for quality control on the data that we're including. And for something like clinical text that we're going to be using these large language models for when we're doing clinical machine learning, right, this might actually make a huge difference. So when building these large language models for text, right, we have to take into account different considerations than somebody doing something for a general application. So to start off, right, I would like to think that all of the stuff that we're doing here matters in some sort of clinical sense. So there are direct downstream users in which if we get a prediction wrong, there is some at least mild consequence. So when we're building these models, we're trying to achieve as high a performance as possible. So we might be willing to make a trade-off in terms of speed or efficiency. Next, when you're looking at large language models, especially like those from OpenAI and even Google, right, we don't really know what data they're training on. And if they happen to be training on data that is either inducing some bias into the model or some other form, right, this could be really impactful and bad for a clinical application, right? If your model has this association with certain populations, right, that might get instilled into the model and propagated down into the healthcare system towards the patient. And I think kind of the biggest aspect of this is that we're dealing with clinical notes. And I'm sure most, if not all of the people here have read a clinical note, and they're really, really difficult to parse. So you first have like all these random abbreviations, especially in nursing notes. And when I'm like personally going through these, I have like one Google tab open and like the nurse tab and like the nursing note open, and it's still often like not enough. Like I can't tell if something's an abbreviation, it's just a typo. I honestly sometimes just have no idea what's going on, right? You have all this incorrect grammar everywhere. They're just like random line breaks because why not? And of course you have a ton of medical terms, right? And this is kind of the big difference here of you open up a note and it's just like medical terms everywhere. And if you look at kind of the text that's being included for a general language model like GPT-4, GPT-3, right, it's all kind of like Wikipedia news articles in which the frequency of that those words, those medical terms appear is going to be a lot less. So the distribution is a lot different. And there isn't exactly an easy solution to this. So when you look at something like PubMed, you can just download that text, include it in your language model corpus. But when you're trying to do this for the clinical space, you can't really include notes. I mean, you could, but you shouldn't. But this is kind of the big blocker here, in that these language models likely don't have any sort of clinical notes in their training corpora. So in this paper, we take the position of you're some hospital, you're the CEO, I don't know, the head of a hospital, and you're trying to accomplish some language modeling task. So maybe you want to summarize notes, maybe you want to do email triaging, you want to classify whether or not this patient will die or not, right? It's just an arbitrary downstream task that takes into account some clinical notes. And we lay out 4 different options that the hospital could take. The first of which is take their local notes in their hospital and train their own language model. And this would be training a language model from scratch. The second option is slightly less computationally expensive, in which you take some general language model that somebody else has trained on the general web, you download it, and then you further pre-train it on clinical text. And this is kind of, the idea behind this is that like it already has some decent understanding of what language is. It kind of can model sentences, but it's lacking kind of the knowledge that a clinical note has. So the solution is rather than pre-train your language model from scratch, you pre-train for a small amount of text on the clinical notes. And this is what the clinical BERT paper did and many other papers have done. And what they pretty much showed is that you do get some mild performance gains. So you look at something like BERT, and then look at the last row of biodischarge summary BERT, and you see some performance gains on most of the tasks. The third option is the pretty lazy option of we're just going to download somebody else's language model, and we're going to fine-tune it for the tasks that we care about. And we're going to fine-tune, I should mention that we're going to fine-tune all of the other models in this setting. And this is kind of like this is like you have a day to do it, and you just download somebody else's model, run it on the fine-tuning data, and then call it quits from there. The fourth option is extremely 2022, 2023, of you just don't care about fine-tuning data anymore. It's too much work to collect it. You just open up ChatGPT and like prompt it, pretty much. And this is only like possible in NLP because realistically, you can frame any single NLP task as a next word completion task. Of if you're trying to do mortality prediction, you just give it the note and then you ask it, do you think this patient will die in the next like 5 days? And this is something that's really unique to language. And the reason we're considering, we're not really considering fine-tuning in this setting is because doing this kind of zero-shot approach typically only works in super, super large language models. So it is extremely computationally expensive to backprop on those language models and to fine-tune them. And then also, it just would add up really fast. And as part of this, we weren't actually able to get GPUs big enough to kind of take into account this setting. And for this paper, we look at 12 different language models. And we actually look at, I think, 5 or 6 more in the appendix as well. But essentially, I think what we tried to do is we tried to include a good mix of clinical language models that were available, and as well as their general domain counterparts. So people who have trained the same architecture on just general text. And for this project, a huge part of this project is that there aren't actually that many clinical models that people have shared. So we had to train 3 of our own for this project. And the first of which is a model that is doing that domain adaptive pre-training. And that is clinical T5 base checkpoint, which is initialized from T5 base and then pre-trained further for 13 billion tokens. And then clinical T5 base and clinical T5 large are pre-trained on Mimic 3 and Mimic 4 for 38 and 40 billion tokens. And that is for roughly 19 to 20 epochs. And the experiments that we're using for this paper are 3 clinical data sets. The first of which is meta-NLI, the second of which is RAD-QA, and the third of which is CLIP. And I won't go into too much detail about each of these tasks, but essentially higher performance, so a bigger number here is better. So when we first kind of look at the results, I think it's important to compare how a clinical model of the same architecture compares to a general model of the same architecture. So when we look at clinical T5 base, what we find is that it's significantly better than T5 base. And perhaps this is unsurprising, right? Because we're training on the distribution of words that we're going to see at test time. Second, we look at clinical T5 large versus T5 large. And we see a similar trend here in which the clinical model is outperforming the general domain model, given that they're the same architecture. And lastly, we look at the setting in which we're doing domain adaptive pre-training, in which actually clinical T5 base, which is trained from scratch, performs actually much better than doing this adaptive pre-training. And this is due to a number of reasons, mostly due to it's really hard to pick a learning rate for doing the checkpointing, in which you have to decide, how much am I going to forget from the general domain and how much I'm going to learn from the clinical domain. And the setting that I'm actually really interested about is how do these models compare when they're significantly more, when you're comparing a size up. So when you compare T5, clinical T5 base to something much larger, because this is a more realistic setting. And what we find is that clinical T5 base largely performs the same as T5 large, which is 4 times bigger. But it does fail to outperform T5 XL, which is 14 times bigger. And we see a similar thing with clinical T5 large, in which it roughly performs the same, if not better, than T5 XL, which is 4 times bigger again. So there's clearly this relationship between training on clinical text and being able to be more efficient in the number of parameters that you have. So training a specialized language model, right, is a really expensive thing, right? It's not easy to say, like, hospital, go train as big of a language model as possible. It's a real difficult task and requires a ton of compute. So at what point is it actually worth it to do this? And I think in the paper, what we try to say is that you can achieve a similar amount of performance, a similar level of performance with a much smaller model, which means that your inference time costs will be a lot smaller. And because you're able to use a smaller model downstream, if you run this on enough nodes, you will eventually recover your costs. And we calculate this out in the paper. And lastly, we get to the setting of in-context learning. So how do we compare to something like ChatGPT? And what we find is that the models that are using in-context learning are on the dash tier. And what we find is that even on training on like 100 sentences, 200 sentences on meta-NLI, and using that only as our training data set, we're able to outperform those models. So I think, despite the fact like these models work really, really well outside of the box, just like you can use them, no training data at all, they are quickly outpaced by much smaller models. So in conclusion, right, if you want that best possible performance, it's really important to train your language model from scratch. It will be a lot smaller, a lot faster, and just work better. And then kind of reiterating that last point, it's really important, if you want the best possible performance of your model in a high-stakes setting, to fine-tune your model for your specific task, because it's really difficult to get high performance using in-context learning. Thank you.
Okay. Question? Oh, great.
Thanks for a great talk. You mentioned that it's really hard to pick a learning rate. I'm just curious, what do people do for learning rate scheduling, or has anyone tried doing like adaptive learning rate scheduling for these large language models?
Yeah, so that's a great question. I think you can measure something like perplexity and your loss, and that will generally be like a good signal. But it doesn't necessarily mean that your model is going to be better at like downstream tasks. So there is that kind of disconnect there. And then it's also just like really expensive to do it, right? Like playing around doing a hyperparameter search of your learning rate is like, at that point, you should just train from scratch. And it would have been easier. But like a lot of the cost in terms of like, OpenAI spending like $1 billion to do this is in like doing the hyperparameter sweeping, figuring out what the right learning rates are. And I haven't seen too much work about like what the actual, like if there's like a systematic way to do it correctly.
Hi, there's one more question here. In addition to context learning, there's a new type of learning which provides a huge context, like a bank of memory, a pool of memory. Instead of training your machine learning model, which is a large language model here, you only modify that pool of memory instead of modify the parameters to achieve like adaptive learning or different results. What's the comment on that?
Yeah, no, that's really come to life in like the last like 6 months. So we didn't get a chance to test it in the paper. I think the question for me, like clearly that works very well. The question for me is that is there something fundamentally different about clinical tasks and that you need clinical knowledge for that clinical task that you can instill to that small number of parameters? Or is the parameter efficient fine tuning that people have been doing just teaching the model how to respond to instructions? Like it's not clear to me that setting aside a small amount of parameters is sufficient for teaching the model like clinical knowledge. So I think a lot more experimentation needs to be done, especially in transferring kind of the stuff in the general domain to the clinical domain.
Thank you.
All right, well with that, let's, you want one more? Yeah, we have time.
Yeah, I'm just curious. It seems like a lot of what you're getting at here is related to the question of scale in terms of number of parameters and efficiency and things like this. And scale is interesting and sort of tricky because it's not necessarily something that that the expertise for scaling things up effectively necessarily lives in, to these degrees, lives in the same areas as expertise for deploying, clinical informatics systems and things like this. And so I wonder if you can offer a comment on, how are we going to balance the extent to which, you can get more efficient if you train from scratch and things like this, but, the reality is OpenAI and companies like this are building stacks that they're highly optimizing for efficiency in a general domain, and it may just be that trumps the fact that even though you could do it more efficiently if you built something in-house, like how does that tension relate to what you're talking about here?
Yeah, I think that's a great question. I think in this paper, it's more of we're taking the perspective of a hospital, but actually we're like researchers, right? Where we're really constrained by resources. And I think the question will be, is there a company that's willing to spend a ton of money to build a large language model? Or is Microsoft going to do something like they're just going to do some domain adaptive pre-training? And I don't think, I think it's about what's easier to do. So I really do think that people are going to kind of shift towards either clinical instruction tuning or domain adaptive pre-training. But it's unlikely that somebody's going to invest as much money as Microsoft and OpenAI into training a language model from scratch, especially because you can't share notes between hospitals. So this is like a unique problem to the US in which like, if you're going to train a language model from scratch, you have to build it for a specific hospital. You can't just build it for all of the hospitals. So I think people are going to run into that blocker really fast, which will make it kind of easier to just do the domain adaptive pre-training in that case.
Great, all right, let's thank our speaker one more time. And with that, we're at our break and our first poster session. So you can find everybody and keep asking all your questions and discussions.
All right, everyone, welcome back to our last session of the first day of CHIL. We're going to have a panel discussion on data sharing, and our moderator is Dr. Marzia Gassemi, who is the Hermann L.F. von Helmholtz Professor at MIT, very fancy title there, with roles in electrical engineering, computer science, and the Institute for Medical Engineering and Science. Her research encompasses representation learning, behavioral and healthcare machine learning, with an emphasis on transforming diverse clinical data into cohesive, predictive patient information. She holds BS degrees from New Mexico State University, a master's from Oxford, and a PhD from MIT. So Marzia, come on down.
So I have now fulfilled one of my life goals, which is to be a contestant on The Price is Right, which is America's game show. The other is to fulfill my American civic duty and serve on a jury, but I will never be chosen. I've heard many other people here have been chosen and know that I'm coming for you because you've stolen my dream. So I am now going to introduce the panelists who are going to serve on this panel. I'm going to introduce John first because he's here with us on Zoom. So Dr. John Halamka is an emergency medicine physician and medical informatics expert. He's the president of the Mayo Clinic platform, leveraging AI, connected health devices, and partnerships to transform healthcare. With over 25 years of experience, he previously served as the CIO at Beth Israel Deaconess Medical Center and International Healthcare Innovation Professor at Harvard Medical School. He's also a member of the National Academy of Medicine. Welcome, John.
Follow all of your guidelines for ethics and goodness.
We are happy that you are. We would not choose anyone else. Next, I will introduce Dr. Ziad Obermeyer, who is an assistant professor and Blue Cross of California Distinguished Professor at UC Berkeley. His work merges machine learning and healthcare. He's a Chan Zuckerberg BioHub investigator and National Academy of Medicine emerging leader. He was previously an assistant professor at Harvard Medical School, and he still practices emergency medicine in underserved areas. So Ziad, please come join us. Next is Dr. Elaine Nosasi, who is an assistant professor at Boston University and a pioneer in utilizing data and technology for health equity. She leads the Racial Data Tracker Project, serves as a senior advisor to the NIH Aim Ahead program, and is renowned for her work using digital data for public health surveillance. She's a champion for representation in data science, holding a PhD in computational epidemiology from Virginia Tech, and having held previous positions at Harvard Medical School and Boston Children's Hospital. Elaine, come join us. And finally, I would like to welcome Dr. Khaled El Imam, who is a renowned professor at the University of Ottawa, a senior scientist at the Children's Hospital of Eastern Ontario Research Institute, and the director of the Electronic Health Information Laboratory. He's a Tier 1 Canada Research Chair in Medical AI and specializes in privacy-enhancing technologies and synthetic data generation. He's a prolific scholar, having had key roles in the National Research Council of Canada and the Fraunhofer, probably mispronounced, Institute in Germany. He holds a PhD from King's College, University of London. Please come join us. So on this panel today, I think most of us here could just repeat the same thing. We probably all agree that data should be used in medical models, that it should be good data, it should be fair. And so rather than focusing on the things that we probably all agree on, I'd like us to discuss some things that are probably less certain and there's more diversity of opinion on. And so one of the things I wanted to start with, maybe the most basic thing, is sharing data. So all of us probably have used real data in our models at some point. We don't usually stick only to synthetic data. And so a question for the panel is, what do you think are good incentives to share data? And what are some of the real barriers, maybe not fake barriers that people put up, but real barriers to sharing data amongst researchers, industry, and different kinds of parts of the process that we look in machine learning for health? Sure. Go ahead. It could be on.
There you go. Okay. I think privacy is a concern, rightly or wrongly. Many data custodians are concerned about privacy and concerned about their liabilities if they share data, and they don't deal with the privacy concerns appropriately. For industry, there is a real concern about revealing proprietary information and the disclosure of IP. So if data is shared and someone discovers something using their data, who owns that IP, and can it be, some value can be given back to the data custodian, so that's a real concern as well. For small organizations, they don't have the resources to clean data, to prepare data, to document it, etc. It's just the funding is not there, the resources are not there, the expertise is not there to do it well, so they just don't do it. So 3 reasons.
So Ziad, can you talk a little bit about how some of your work with Nightingale and Dandelion has tried to move past these barriers?
I appreciate how you framed it up front as at least in part an incentive problem. So I think that there are, and Khaled, you're working on a lot of technical solutions that try to get around some of those trade-offs. But I think sometimes there are still going to be cases where you need the real data, and that is really an incentive problem. And so I think that this looks like a fairly classic public goods problem where there's you have this resource, the data that's locked up inside of health systems that has enormous benefit to society, but you have people who are the gatekeepers of access to those data who are not necessarily privately incentivized in the same way that the rest of society is. And so how do you figure out how to make sure that the incentives are aligned? We've found 2 ways. And so there's a nonprofit that I co-founded 2 years ago called Nightingale Open Science, where we raised a lot of philanthropic funding. And then we found one person at a hospital, and that could be like someone in the C-suite. So at a county hospital that we worked with, they were very concerned about underdiagnosis of heart disease. Or it could be a researcher. Another organization we worked with, large cancer center, they had 10 years worth of whole slide images that were literally gathering dust in their basement. And so we were able to deploy philanthropic funding to scan all of those slides or to collect a lot of data from that county health system, get their ECGs and echo data online. We were able to de-identify those data as one layer of protection and then move them over onto our cloud where any of you can actually access those data for free at nightingalescience.org. That's one model. I think the second model is that health systems are in this funny position where they are supposed to be producing health, but they're supposed to be producing health within a weird financial system where they also need to figure out how to get reimbursed for producing health. And so the second organization that is a for-profit that I co-founded and I'm conflicted because I hold equity in, it's called Dandelion Health. We work with large non-academic health systems from a diversity of places that serve a diversity of patient populations across the US. And what Dandelion does is it pools data, it curates data, and it makes those data available to people who want to develop or validate AI products. And the way that works is that we essentially are in a partnership with those health systems where we share the revenue from those activities back with them. And so we didn't go to them and say, we will give you X dollars for your data, because I think what a lot of people have found is that no matter what X is, everyone thinks it's worth 10X. And so what we said to them was like, look, we don't know what the data are worth to people who are going to pay with it. We know that it's worth a lot to society. We're going to go find out what X is, and we're going to share half of it with you. And so I think those are 2 different ways to make those incentives align and to unlock the enormous value of this data. And I think this is not to minimize there are clearly privacy issues, and we solve that with different layers of protections from legal to technological to kind of not letting the data leave our environment. And I think that that's an important thing to take into account, but we also need to take into account that these data are enormously socially valuable. If we had diagnostics for cancer before the cancer metastasized 1 year earlier because the data got into the hands of a researcher faster, that's worth a lot to society. So it's a trade-off.
And Elaine, what are your thoughts about these incentives and barriers on data sharing from a public health perspective, thinking about the ethics of doing so?
So the AIM project, which stands for Artificial Intelligence, Machine Learning to Advance Health Equity and Researcher Diversity program at NIH that was started a couple of years ago. The focus is one, to increase representations of individuals and communities that are underrepresented in the development of AI models for biomedical research. And the second goal is to increase diversity of the data sets that we use in training AI models for biomedical research. And a lot of that focus is going into those communities and having conversations with them. So we're working with HBCUs, Hispanic 7 institutions, tribal colleges, and most of that conversation is centered around trustworthiness. So how do we build trust in a way that these communities feel that they can share their data with individuals developing AI models? How can we make sure that data is not misused or used in a way that comes back to affect them in a negative way?
And John, in the conversations that you're having now, what are your thoughts on these different perspectives about the incentives and risks for data sharing?
Well, so your panelists have really teed it up perfectly. There are challenges as we think about doing goodness for society with the corpus of data of the past so that we can predict the care journeys of patients going forward. So you could centralize the data. You could sell the data. You could decentralize and federate the data, right? As you say, there's a huge diversity of approaches. Mayo's approach has been every organization that participates curates their data into an OAuth++ format using a FHIR approach for data exchange within their cloud container. They decide how it's used, who it's used by, they audit everything. So you solve the technology, the policy, and the psychology issues by reducing some of the risks around privacy breach or IP sharing. There's no one right answer to all this, but our approach certainly of decentralized and federated has worked pretty well.
So moving on from sharing data, how do we feel about sharing models? So, this is maybe particularly relevant now that we have large language models or other transformer models, really high capacity models that have been trained on many examples, billions of parameters. Where are the risks and the incentives there? And also, there's many different models for sharing models. You could open source, you could release pre-trained models. There's different ways of trying to ensure privacy of the data when you release either. What are your thoughts? Start with, yes, Dr. Ilham?
Yeah. You have the privacy issues with models. There have been some discussions in the privacy community about treating models trained on real data as personal information. So that's going to be an obstacle if that takes off, because because the adversarial attacks on models, if you're able to recover personal information, you start treating models as personal information and then regulate them as personal information, that puts a lot of obligations on top of the use and disclosure of models as well. So that's one thread that I think is worth following. The regulators are becoming more strict and increasingly concerned about use of and the sharing of machine learning models. And then the other one, the obvious one, of course, is generalizability and taking models from one place to another and how much you can trust those results. And I don't think we've solved that problem yet.
So there are definitely short-term risks to releasing models and privacy risks. What about longer-term risks of not releasing models? What kind of dangers are there from not having these models open widely or available widely to people in different places? Ziad or Elaine? No, you do it.
All right. I think that it is, everything is a trade-off, and there are risks to releasing models. I think I agree implicitly with your framing, Marzia, that there is a much bigger risk of not releasing models, or at least not having ways to audit their performance. I think it's a very funny situation that when you're looking around, there's like lots of different people who are predicting ejection fraction with electrocardiogram waveforms. And a weird thing is that even though there is one number that could tell us how well those algorithms are performing and which one is the best, and we have this leaderboard culture in lots of parts of machine learning, there's no way to do that right now. And so I actually think that that's a huge problem for not just for the market working well and people buying the best algorithm and competing on accuracy, which is what we want them to, but it's also a problem for equity, because I think a lot of these models are trained on data from academic medical centers, and we just don't know how they're performing at not academic medical centers because there's just no way to get data. And so I wanted to highlight some work that actually we've been doing with Alistair, who's here, at this company, Dandelion, where we're actually building an infrastructure where people can upload an algorithm in a container. They retain all the rights to that algorithm, and the only thing they authorize us to do as a company is to run that model on our data, on whatever label they choose to evaluate it, and we will send them back a performance report on how well that algorithm is doing overall, and because of the diversity of our data set, how well that algorithm is doing on really important underserved groups. And I think just on a personal note, as someone who's written a lot of papers about how racial bias gets into algorithms, one of the things I've learned over the past year that's been very gratifying from being involved with this company is that when you're working in this private sector environment where things happen in finite time, you can actually do something concrete rather than just writing another paper, which is what I otherwise would have done with that time. And so that was very satisfying.
I think some of the conversations around generalizability in public health is mostly focused on the fact that a lot of the issues we have in public health around equity come from that assumption that we can generalize everything. If we build a solution for one group, it applies to all groups, which is usually not the case. So there are many people who are making the argument for building models that are specific to specific populations, or at least adapting models to specific populations, so we're addressing the needs of those populations rather than assuming that one model applies to all populations.
And John, what has been your perspective on looking at these different risks? So sharing a model, right, where there might be some risks depending on how exactly you release it, versus the risk of not allowing other people to use a model when they might benefit from it.
So Casey Ross, a journalist at STAT, wrote, "Healthcare AI has a credibility problem. And the only way to get beyond the credibility problem is to build transparency." And this organization called Coalition for Health AI, several of us work on that, said we need to look at transparently, as Dina has talked about, measuring fairness, appropriateness, validity, equity, and safety. Make that publicly available. So either the model is available or all the metrics are publicly available. Chuck Schumer yesterday, I'm sure you saw this, said, well, for the country, when he said we need to be able to explain AI, he didn't talk about true explainability. It was more how is the model developed? How does it perform? Does it have data shift? Is it likely to be useful for a given population in a given geography? So I think we're seeing not only the technology, building assurance labs, but policy at national scale evolving to build the transparency we're lacking.
So can I just follow up? I mean, we haven't reached a consensus on appropriate metrics to compare and evaluate models, and we're talking about fairness metrics, privacy metrics, performance metrics, et cetera. So there's some effort needed there to reach consensus on benchmarking, developing benchmarks and metrics to evaluate and compare models. But the other thing about sharing models is, our hypothesis has been if you train models on synthetic data, then you can share them. So to the extent that synthetic data can allow you to build models with the same performance as models with real data, that solves the model sharing problem to some extent, in that you address the privacy concerns when you make those models available to others.
So one thing that I think comes out of both of these questions, with difficulty of sharing data, potential difficulty of sharing models, whether synthetic data can achieve the same results, all of these different things we're thinking about, is what should some of the policy considerations be for these very human problems that occur in academic settings, corporate settings, hospital settings, such as what do we do if somebody wants to opt out, right? How do you actually turn that into a true opt-out later after a model has been trained? Or some of the questions that we talked about previously are, what is the right context for using this data? So as John said, if you say that I have a specific data set and you're optimizing for a specific outcome, is that actually an appropriate data set to be learning on for a specific outcome? And there's many different ways to think about that. What are some of the policies, or maybe the one policy that you think would be very important for improving trustworthiness, transparency, and not explainability, but like the explanation of why people should trust AI in health? One from each of you. Your favorite.
It's not a simple answer. We did an analysis a few years ago with a group of lawyers on deleting or removing your data under English common law and under the GDPR. And it's very complicated. Withdrawing consent is very complicated. Under what conditions? Depends on how you obtained consent. whether it was an opt-in consent, an implied consent, deletion, or not using the data anymore for future studies. The rules around that are actually not straightforward. They're quite complex. So we have rules, but it's not straightforward, and the lawyers themselves don't always agree on how to interpret the laws in terms of withdrawal of consent or removal of data or deletion of data or right to be forgotten and all of these things for health data and public health purposes. The other consideration is you have ethics review boards or IRBs who have to contend with those things as well, in terms of if you're collecting a registry or a repository, how do you deal with individuals who want to withdraw their data? And so I sit on the ethics, the panel for research ethics, which advises on the ethics policy for Canadian research, and that's something we grapple with. The answers are not obvious. How do you what's the guidance for ethics, research ethics boards to deal with this? So I don't think there's an easy answer.
So not an easy answer, but something definitely that's important to think further about for each context. And then Elaine or Ziad or John, do you have thoughts about what is one policy that you'd be interested in seeing more work on, maybe around making sure that learning is done in context, in ensuring that there's diversity of sample data, anything that you think is most important right now? I'm going to give you both a microphone.
But I'll be happy to jump in. So the question of consent and informed consent is one that's tricky. And as we've been chatting about, ensuring we tell our patients, make a promise. When you come to receive care, we would love to use the data of your experience to inform the experiences of patients that come after you. We will never sell your data. We will never exfiltrate your data. Is that okay with you? And you can opt out. And this is what Mayo does today. And at the moment, the opt-out is really binary. Either you're in or you're out. But we think that there's probably a little bit of granularity to add. Might be that you're okay with your general medical record, but not your behavioral health or substance abuse or sexually transmitted disease data or genomic data. And how do you get that balance right of giving patients transparency and control, but do something that's actually implementable and supportable? And as was just said, redacting data once a model has already been trained on consented data is an unsolved problem.
I'm going to call on Elaine because she's got the mic. What do you think about how ways that we can ensure that models that are trained on data that's actually appropriate for that question? Where do we draw that line, and how can we try to enforce that? And in what communities, right? This is like a multifactorial optimization.
I think it's maybe easier to, like, when we start with a question rather than with a model, it's easier to identify what data sets you would need to answer that question. But if we start with a model, then we're just throwing things at that model and trying to figure things out. So if the question is coming from a problem that's within a community, then obviously you want to think about what are the data sets that you need from that community. And building trust with communities takes time. So if you're trying to solve a particular problem that affects a particular community, it might take you years to build trust. It might take even more years for you to get access to that data. And so it's something that in academia that we don't get the flexibility to do with our research. Community engaged research is not something that we're usually encouraged to do because it takes so much time for us to do. So we're always looking for data that someone else has already collected, or data that's already available in the system. And sometimes the data sets that are available have so many gaps that they end up creating more problems than actually solving problems.
And Ziad, do you have thoughts on, I think that's actually a huge problem right now in academia, as you've both noted. We're not incentivized to collect and curate the right data for the actual problem that we want to study, because it's often very difficult to do and maybe impossible depending on your academic timeline. What are some ways we could think about moving forward and getting around that?
Yeah, I couldn't agree more with that. I think so often the work that we do starts not with what are interesting or important problems we can solve. It starts with, well, what data do I have available that I can do a project on in the next 5 years? And I think, unfortunately, because of, and I think I always think, John, about how amazing it was that whenever you signed that first paper for the mimic data set, like, it was just kind of a minor miracle that happened, and so many papers have been written since then, which is great if you're interested in anything related to the ICU or the ED that you can speak to in that data set. But there are a lot of other questions that that we might want to answer that aren't there, and so I think that a lot of the work that I've been doing has been trying to make it easier to start with interesting questions and then go from there rather than start with the data. I think some of the other issues that, having listened to great answers from others, I'll just contribute one thought about the policy. I think that if you put yourself, if you imagine you were at the FDA and it was before we had our current policy about drugs. So the policy on drugs is actually pretty clear. It's you have to specify your primary outcome that has to be measured in a certain way, and then you have to run a trial that shows that the treatment group is better than the control group. And it seems so simple now, but I think before we acquired that vocabulary and methodology for describing things probably looked very similar with drugs than they did with AI today. There's a bunch of exciting stuff going on, but there's also some crazy stuff that is really unsafe and bad and unfair. And I think that that's where we are now with AI. And I think thanks to, again, John, you mentioned this the CHI coalition. I think a lot of other people are starting to put into place a nutrition label idea or some set of metrics that involve, okay, what is this algorithm supposed to be doing? How does it actually perform with respect to the thing that it's supposed to be doing? How do we hold it accountable? I don't think everything has to be done in a randomized trial, but I think that's certainly important when you're dealing with a high stakes label. So I think helping the FDA and other regulators get that vocabulary and methodology in place is super important. And I think that's a place where academics can really help. The other ingredient, of course, is data. It's really hard for the FDA to say, go evaluate your thing on third-party data that your model has never seen, because where do you get that? And so I think that that's another important place that we're trying to work on.
No?
Well, I mean, I just have one comment about academics advising regulators. I mean, you made the point that you write papers as an academic, and you've had the experience of applying what you research to your research, and they're two very different things. So regulators need to be taking input from a diverse set of stakeholders. I think it's the outcome from having academics only advising regulators is not always the best outcome. You really need a very diverse body of inputs. And so for AI, you also, to the extent that AI will be regulated, you do need a diverse set of stakeholders providing input on that as well.
So currently, a lot of the advice that we're seeing regulators get is from the very companies that make the tech. And they seem to be very happy to be getting regulation advice from the people they might be regulating. So what are some thoughts that you have on things that should be prioritized, either on the academic side, on the regulatory side, on the funder side? There's many ways you could think about prioritizing practices that would make data sharing or model sharing or tool deployability more safe, more advanced, and more generalizable. What are some things that you think should be prioritized in the near term and then potentially the far term?
I think
Can I start with a dream?
Yes, you may start with a dream. Go.
So here's the dream. So a few nights ago, Rob Caleb called and said, so if the FDA were to do those things to enable everything Marzi just said, what should they be? And I said, what if the FDA came up with a set of metrics, right? We all got together, we all agreed on what the common things to be measured would be. The FDA would then authorize assurance laboratories. There'll be one at Mayo, there'll be one at Stanford, there'll be one at, Ziyad's Dandelion, there'll be many of these, right? and that we will run the metrics against large data sets with depth, breadth, and heterogeneity, and we will publicly report those metrics to a nationwide open source registry, a kind of GitHub, so that you could then say, oh, I now have a patient in front of me who's an 86-year-old diabetic female with hypertension. What's a model likely to be useful to this person in front of me? Oh, I go out to the nationwide registry, pull the model down, execute it. It's all FDA approved, compliant, and transparent, and goodness happens. There's the dream.
That's a good dream. How do we get there, Ziad?
Oh, I mean, I think just the core of that vision I love. And I think the reason I love it is because companies are always going to try to influence regulators, and that's, that's just the way things work. And I think the remedy to that is to try to make the market work in a way that is that benefits consumers, and in this case, patients and doctors. And how does that work? Well, the way it doesn't work is if the companies are competing based on monopolized data that they have access to and nobody else has access to, and nobody can see how it's working. And nobody can say, oh, this model is doing this well and this model is doing this well. Like, that is not the basis for a well-functioning market, when there's, essentially like luck and privilege that's dictating how this competition is happening rather than performance. We want companies to be competing on transparent performance metrics, not just on having access to like the biggest data set because they could buy access to the biggest data set. And so I think that like having the core of that vision be around transparent performance metrics, not just overall, but with respect to the particular underserved groups that we care about the most, I think that's absolutely the way forward.
Awesome.
Which brings us back to democratizing access to data to enable the market to function so that everybody has access to good data sets. But the other thing is compute as well. And you also need somehow to democratize access to compute so that you don't have a few large entities with enough compute to really innovate and build these models.
Taking a more broader view beyond health, so thinking about maybe large language models and where that data is coming from. So the individual, especially when you think about data for different languages that are being collected in the global south. People are spending so much time to collect that data, and it's being used to train models without them ever receiving anything for that. So who actually gets rewarded? It's something that we should be thinking about.
So I'd like to close with a question that's a little bit more open. And so in the context of the topics we've covered in this panel, can you tell me either one thing that you're very excited about working towards in the next year or two, or something you're terrified of that keeps you up at night in the next year or two?
I work at a children's hospital, and so we have the problem of small data. A lot of pediatric data sets are very small. And so some of the things we're working on is data augmentation and different ways to enable you to build machine learning models when you have small data sets. And this is not just a problem in pediatrics, it's also a problem with rare diseases. I think it's a very important problem, and so we're looking at it from a perspective of synthetic data and generative models as a way to simulate additional patients based on what you learn from our hospital's data and other hospitals' data, and to see if we can build models that approach optimal models that you would build had you had access to all population data sets. So that's my plan for the next year.
Okay, something you're excited about. Elaine?
I'm working on social determinants of health data, so I'm very excited about how to combine, how to use machine learning and AI to produce better data for social determinants of health, but thinking about it from a policy perspective. So how have policies over time, especially thinking about historical policies, shaped health outcomes for different populations in the US, and how can we better understand inequity in the US so that we can create better policies in the future.
Nice.
I'll start by just observing that probably all of you share some of this experience, but by virtue of being, like, I am in this room because I've been incredibly lucky. I have won multiple lotteries that gave me access to data and people to work with the data and collaborators and colleagues who have taught me a lot. And I think that, I often have this, like I used to, PhD students at Berkeley in EECS or stats would come to me and say, oh, I know how to do this cool technical thing. I'd like to apply it to health. And I'd say to them, great, well, we'll get you fingerprinted and we'll get your tuberculosis test done, and then we'll add you onto the data use agreement. And it's like, by then they're already working at Meta, like optimizing.
Facts. These are facts.
Optimizing ad clicks or something else. And I think that, because of lots of interest in making compute and data and beyond what any one person is doing, like, I think there's just a lot of attention to the need to get more people in and to have a bigger tent, and I'm seeing that already. And I think there's a lot of I have a lot of optimism that over the next few years there's going to be not just more people working on these really, really important problems, but just different people who haven't benefited from all the things that I've benefited from, and probably most of you have benefited from as well, to be in this room. And I think that's very exciting, and I'm optimistic about all of the new problems that those people will be working on and solving.
So we have 3 wonderful, optimistic hopes. John, what's
Why am I so excited? Although the pandemic was a tragedy, it did one really important thing. It brought us all together and showed us that we can only solve big problems if we work as a community. I would argue the competitive angst across academic institutions, across industries, is melting away. And the ability to bring together large data sets from heterogeneous sources around the world, bring companies together to solve some of the challenges we've described today, easier than ever before. What does that mean? It's democratizing access to the clinical knowledge and to the models. I even see us getting to the point of looking beyond some of these academic institutions into the community and giving them the models as AI starter packs for free. It's the only way we're going to transform healthcare nationally and internationally. It's all starting to happen.
All right, well, thank you to this panel for giving us all of these things to think about and think through. I think we're close to time, so I'm going to ask for a round of applause for our panelists. And if you have other questions for them about data sharing, about model sharing, about how best to make sure that we are moving forward towards some of these very positive outcomes that they've all envisioned, please find them at the break. Thanks. Oh. Okay. We do have audience Q&A time. So if you have a question for any panelist, please ask.
So, is the mic on?
Yeah.
So, John, I also really like the core of your dream. I'm curious, the assurance lab idea kind of sets you on the right course for that first initial validation. But when you start to think about the subsequent deployment, the subsequent ongoing monitoring, retiring of models and replacement of models, how do you start to think about what's the dream of building out that infrastructure so that that can be done outside of Mayo, outside of MGB, at the smallest hospital or health system? I'm just trying to figure out, like, assurance lab is good step 1, but what comes after for deployment and safe ongoing use?
So I'm sure all of you have read the FDA's predetermined change control plan idea.
Of course.
Commercial product. Yeah. But the idea that a commercial product is never going to be static.
Right.
And what that implies is that when you get FDA 510K, you file a plan that says, and we, the manufacturer, will ensure that every quarter, or whatever the right interval is, it is going to be retested. And we're going to make the following improvements. We're going to use the following validation the FDA over the life cycle of this thing being used, and FDA in return will give them the capacity to constantly improve it without having to go through 510K from scratch, as has happened in the past. So that's good. Rob Kalo said something kind of interesting. He said, you know, in Israel, if you say, pick some intervention, COVID vaccines, 2 months after you give them, you can actually say it worked. In the United States, we still don't know. So how do we instrument every healthcare delivery organization to have some kind of outcome measure so as AI is deployed, not only is there monitoring at the product level, but you have an understanding of what actually happened to the patients and did harm occur. And that has to be continuous.
Ed?
Thank you for the great discussion. I have a question for Dr. Obermeyer. So I love the idea of revenue sharing with the hospitals to get access to the data. I think that's one of the most viable way to get access to data. Was during the contract or the discussion with the hospital about revenue sharing, was revenue sharing with the patients also a consideration factor? And do you see that backfiring at some point because you only share the revenue with the hospital, but it's not going back to the patient who's also an owner of the data? So just wanted to,
Yeah, I mean, it's a really important question because I think going back to how, Marzia, you opened this discussion, it's what are the incentives? And so I think that what the problem that we were trying to solve was that the gatekeeper for the data, the entity that basically has to have the incentives aligned is the hospital, because the patients have already, signed the consent form that gives the hospital the right to do, reasonable things with the data. So that's the cold problem-solving way of looking at it, but it doesn't really address your question, which is like, well, but it is the patient's data. And so I think that so I'll tell you how we're thinking about it. I don't know if this is the right way to think about it. I think this is a really complex area with a lot of trade-offs that I don't know what the right way is. But the way we think about it is that clearly, of course, on some level, the data that pertains to you, your laboratory values, it's your data. And you should have a lot of say over what happens to those data. I think there's another level on which it's actually all of our data as well, because all of us are paying for these data to be created via insurance premia, via taxes, so even though, of course, it's your data and the privacy and agency issues are really important, it's also it is a public good in that sense. And so we try to be good stewards of that public good on a project by project basis. When someone comes to us and proposes something to do with the data, we do effectively the same cost-benefit analysis that an IRB does, that the Belmont Declaration lays for, that the FTC, when it's evaluating AI products in other areas, which is do more good than harm. So we don't approve any uses of data that don't have patient benefit. Now, it doesn't have to be benefiting the particular patient who gave the data, because I think that's just a really hard set of pipes to connect up. But I think the general principle of doing more good than harm, which all of us, when we're wearing our research hats, like no use of data is without risk. Even when you're, a mimic, using mimic data is not without risk. But we do it because the potential to discover new things is worth the level of risk that produces. And so that's the general calculus that we try to make on a project-by-project basis. The hospital systems make that on a project-by-project basis too, so they can veto any use of the data that they don't feel comfortable with.
Thanks. Great discussion. So I really like the idea of kind of like a leaderboard and the auditing system that you all are discussing. And I'm wondering how it relates to kind of healthcare in general. Like I'd love something like that for doctors. Like, who's the best doctor? Are they available? Type of thing. And it kind of seems like, can we develop such a system for healthcare in general? Is that possible? And if so, is it that doctors are fighting we wouldn't want that? And would we get the same thing from AI companies? And how do we kind of think about this in the bigger ecosystem?
So I have said often, it's really funny that we're all worried about AI that's been trained on medical data, killing us, because the only reason it will is because doctors are doing it right now. But I think that one of the really great things about training AI on medical data is we're now all thinking about medical data and what all of the inefficiencies and gaps in medical processes are. There are some subspecialties of medicine that do have scores, right? So if you perform a surgery and then there's a surgical site infection and the patient is harmed from that. And there have been some analyses from health economists or others who have looked at, for example, state level errors at hospitals, that medical errors that have resulted in patient harm. And those estimates tend to be fairly consistent. To my knowledge, nobody is suggesting yet, other than me in my sort of minority dissenting vote, that there is also a scoreboard for clinicians in the same way that there for some subspecialties is a scoring. But maybe Ziad or John might know if this is part of the conversation.
I think there's a...
I think measurements and comparison is just hard, right? So, Ziad, you're an emergency physician, I'm an emergency physician. Do you know that my patients are sicker than yours? Which is why my quality scores and my costs are a little higher. But you really can't compare because mine are sicker, always. Right? So I think it just, report cards are not great. But what you could imagine is the following. When you pick up your phone and you say, I need an app for something, you go out, you try a few, and you use the one you like.
Right.
And I'm hoping that we all, with this transparency and the regulatory framework we've been talking about, we'll all go out and get the apps, we'll get the models we think are good, and we'll use those, the market will decide.
I think one of the reasons that the leaderboard culture is so strong in machine learning is because in machine learning, we are usually trying to predict a thing, and that thing is fundamentally, it's empirically observable. Whereas, as John was saying, you don't see what would have happened if John's patients had seen me instead. And so if you just compare John's outcomes, they look bad. But if they'd seen me, they would have been even worse. So I think that that's what doctors often say when they see these ratings. And it has been tried. There was a famous experiment with cardiac surgeons in New York State where the mortality rate after surgery was published. And that had very mixed results as far as penalizing doctors who saw very sick patients because their mortality was bad. And so it's a lot more complicated to do it with doctors than it is for algorithms because of that causality versus prediction distinction.
Thanks.
So I've been sensing that there is a recurring theme of data being locked and not readily available to most of the general public who wants to work on clinical data. And I think you did mention just before that you believe that hospitals have their own set of clinical data and that they would prefer not to share it. So what incentives would each of you think would push hospitals to be more public about their data, of course, like after it's been de-identified?
So I get to live this dream every day. And when I go to hospital systems and say, do you want an algorithm? And the CEO says, I can't even spell that. Well, CEO, what are your challenges? Well, my margins are negative, my staff is burned out, and I can't hire and retain the specialists and nurses that I need. And I said, well, what if you joined a virtuous network of peers working together to contribute data, validate models, create new models, and it's going to address those three things. And we're going to do it as a community. They say, sign me up for that. So solve one of their real business problems and they're
So I would just like to note that if anybody else would have said that, I would have said it's not possible, but John can do anything. not only is he who he is, he made a joke during a lecture he gave for my class about horse medication, and I told him that was a really weird joke. Where did that come from? He said, oh, I run a farm on the side in 100-acre wood, and you should come see it, and I did. It's amazing. So not only is he who he is professionally, he also runs a shelter for abandoned animals. And my advisor, who was also his advisor at MIT, told me that John was the only PhD student he ever supervised who was bored by the MIT PhD and had to do more. So I think we can all believe in this vision.
Just to build on that, I think one of the metrics has to be cost savings from using data and building models and applying models. And once you demonstrate an ROI from using data, it becomes an easier conversation with the leadership to make more data available and to grease the wheels, so to speak, to be able to reuse data and share it more broadly.
I do have to say, I have personally encountered a lot of data oligarchies in health. I think that there is a culture in some health systems of, I might be sitting on oil, and so I don't want you to mine. And so I don't think all of the caution that is taken with data sharing has to do with real concern for patient privacy. Certainly there is concern there, but I think sometimes people don't want to share.
I think the mining analogy is actually very apt because even though, yes, the oil is very valuable, mining is a very expensive business. And I think that anyone who's tried, I think, if you're just working with the Epic data, yeah, okay, you know where that lives in one place. If you want anything else, like if you want ECGs, or if you want inpatient monitoring data from those bed monitors, you need to have someone at the health system figure out where that lives. Is it getting overwritten every 24 hours by new data that comes in? How do you stop doing that? How do you get access to that remotely hosted server in Kansas City that nobody has admin rights to, and that it's completely unclear what's on it, how many years? So it is, I don't think it's that they don't want to share. It's just really costly from just a money point of view and an attention and priority point of view to actually get the data out and into a meaningful form where it can be used. And when, as John pointed out, that it's not, running a hospital system is not a high margin business. It is a negative margin business, and they are constantly struggling to survive. And it's just it's tough. So I have a lot of empathy for the people who run health systems and have to make these kinds of trade-offs. I think they all believe, everyone that I've ever talked to is really positive about the future. It's just but right now I'm in a constant crisis mode, and you're asking me to take time away from a bunch of stuff that I really need to do something that's going to build some bright future in 20 years. It's a tough sell. So I think it's kind of a miracle that this is happening at all.
And maybe we have a final question.
Thank you. So we talked a lot about aligning incentives for data sharing, but I'm also interested in incentives for model sharing and for also deploying models. A lot of times it seems that there are models that have been widely validated, but they're not implemented because there's a gatekeeper EMR system that doesn't let that in. And then there are commercial entities that train models that no one has seen the data for or the validations of, and they get implemented and deployed in health systems. Should there be some sort of a duty to transparency, at least when public data is shared with commercial entities for model deployment?
It's a good suggestion. What is the panel's thought?
I would say working on value capture is certainly important to think through, which is it a revenue share? Is it the notion of those who help develop get equity stakes? Somehow this idea that we're all incented to do this together because there is some concept of value sharing to work. Nick Shaw is sitting in front of you, and he would tell you of the models he's experienced in the world, 2% are actually deployed in practice. So this is a problem that we all have to solve.
Other thoughts? No? All right. Thank you again to our panelists, and thank you, John, for zooming in from your tight flight schedule.
Hey, I boarded in 2 minutes.
Okay. All right. Thank you again.
All right, so thanks everyone. That was the end of the first day. We'll be back here tomorrow. And I think we would like to invite you all to attend our reception for the next hour in the lobby. So thanks.